Hey everyone, how are we going? Feeling very nervous, Danny, but no, going well. All right, wonderful. Welcome everyone to the Skyline Hatch VCE exam revision series in partnership with UBS. My name is Josh and I'll be taking the chemistry session today with the wonderful Nan as my assistant tutor. Before we begin, I'd just like to acknowledge the traditional custodians of the land on which we gather today. I'd like to pay my respects to the elders past and present, for they hold the memories, the traditions, the culture, and the hopes for Aboriginal and Torres Strait Islander peoples across the nation. I would also like to begin by thanking UBS for their incredible support. It is thanks to UBS that we're able to run this revision series for VCE students. And we also have some amazing volunteers from UBS throughout most of our lecture series who've been able to help and answer questions. Thank you very much, UBS. Wonderful. So welcome to the VCE revision series. Very, very exciting. And obviously today's content is chemistry. So this is set up in a webinar fashion. So you're able to hopefully see the screen and see all of us. And it would be great if we use a Zoom chat primarily for immediate questions such as tech difficulties or anything immediate. And we're going to be using Mentimeter, another program that you're able to access through your phone or through your laptop or through your desktop to ask and have questions answered through that process. So it'd be fantastic if everyone takes a couple of minutes now to go to www.menti.com and use the code H5852277 as on the screen. Once you've done that, you'll be able to see a Q&A section with the question, welcome to Skyline Hatch Revision Series. How are you feeling? It'll be great to see some answers, and I'll briefly share my screen. Oh, amazing. We've got some excited, some tired. A lot of stress, it appears, but good to see people are energized, nervous, that's fine. Sleepy, 10 a.m. But hopefully we'll get everyone pumped up and get everyone feeling good today. Nan, what are you seeing? What are you thinking?
Sorry, can you hear me?
Yeah.
Yeah, there's I'm actually excited for this, and I see a lot of stress, and that's good. Excited is one of the bold one. Yeah, good luck everyone.
Yeah, fantastic. So it's that time of year, it's crunch time when it comes to VCE, and it's been obviously a very tough year for everyone. So it's completely natural to be feeling stressed or nervous, but hopefully today, with the content we go over, the questions we go over, and the skills we share, and the tips and tricks that we've included in today's session will hopefully help alleviate some of that stress and set you up well for the coming few months. Fantastic. Alrighty, so just a bit of an introduction. So the Hatch program, Skyline Hatch, is a complement to classroom learning that helps equip you with tips and tricks to help achieve your VCE goals. So over my period at Skyline, I've been there to help provide VCE masterclasses, weekly tutoring, mindset programs such as Stress Hack for VCE students and schools across Victoria. And there's a variety of very talented Skyline alumni, such as Nan and their peers, as inspirational role models, tutors, mentors, and coaches. And so Skyline Hatch is a new social enterprise with profits invested back into Skyline Education Foundation. This means by signing up to Hatch classes, you are supporting the Skyline Education Foundation to help more young people reach their full potential. Alrighty, a bit of an introduction. So 2 very funny pictures there. Hi, my name is Josh. I'm 21 years old, and I graduated all the way back in 2018. So a little older now, but I've been doing this for a while. I achieved an HR of 99.85 and a raw 48 in chemistry. Apologies, it's supposed to be chemistry. Chemistry is one of my favorite subjects in high school. And I think it's an amazing subject because the breadth and depth of content is so huge. But as soon as you're able to tackle some of those bigger areas of content, those bigger questions and more challenging questions, you're able to do everything. It's one of those subjects where, sure, you step in and there seems to be so many things you have to know. But as soon as you know the tips and tricks, as soon as you've done the questions, I think it's much more like plain sailing than it first appears to be. I'm currently studying a Bachelor of Medical Science and my Doctor of Medicine at Monash. And my fun fact for the day is I once did an eating challenge on Facebook Live last year over lockdown, and that there is a picture from it. Quite disgusting. I do apologize. Nan, take it away.
Okay, hey guys, I'm Nan, and I graduated last year, and currently I'm studying Bachelor of Science and Bachelor of Biomedical Science at Monash also. Yeah, I don't have any fun facts, sorry.
No, that's so all right. Awesome. Okay, let's jump into today. So today we're going to cover a wide range of things. Obviously, this is VCE Chemistry. Hopefully we'd cover a wide range of things. But we're going to start off with a bit about energy and fuel. So a bit of introduction way back at the start of the year. And then jump into everyone's favorite, a bit of equilibrium rates of reactions before we do a bit of a Q&A session. We might do a bit on study and exam planning through that Q&A session, but then run into organic analysis and finally finish up with food chemistry. Before we begin, I always like to give a bit of an overview of the actual study design, because what a lot of people don't know going into VCE Chemistry is that there's actually a set curriculum you have to follow. It's not just, the examiners aren't reading your textbooks and saying, oh, okay, this textbook has this question, let's put it in. The textbooks are written off a set of guidelines produced by VCAR, and those guidelines say essentially what can and can't be examined, the scope of what's examinable. So let's start off with Unit 3. Unit 3, Area of Study 1, Energy Production, which details obtaining energy from fuels, combustions, and also change in enthalpy. A little bit about fuel choices, but the thing people most often struggle with is galvanic cells, redox, the electrochemical series, and of course, everyone's favorite, fuel cells. Nan, what did you think of Area Study 1?
I think it's a bit chill. It was more of heavy contents than the second area of study. Yeah, but I think I liked area of study 1 more than area of study 2. Yeah.
I think you hit the nail on the head there. I think it's very heavy in content, but compared to area study 2, yields reactions, I feel like the maths and the chemistry is much more complicated. There's not as much to know. So this is rates of reactions with reference to collision theory, equilibrium, and everyone's favorite, the Chatelain's principle, and a bit about electrolysis and rechargeable batteries. We then jump into Unit 4, Area Study 1, which I think is the biggest section and arguably the hardest section of the VCE chemistry curriculum, carbon compounds. And this ranges from everything to do with the carbon atom to the properties of different organic compounds and naming, to the analysis of carbon compounds through IR, NMR, mass spectroscopy, chromatography, and volumetric analysis. Finally, we finish off with quite a nice area that's a bit more biological than chemical, and that's food chemistry. So the basics of proteins, carbohydrates, triglycerides, the metabolism of food, enzymes, and the energy content of food with the principles of calorimetry. Fantastic. So a bit of an overview, and hopefully we've all learned a little bit of, at the very least, a little bit of all of these areas through the year, but we're going to revise and cover everything today. Now, before we begin, let's just do a bit of a scale on Mentimeter. So I'm going to move the Mentimeter to our next slide. Move Mentimeter to the next slide. How confident are you feeling for the chemistry exam? 0 being, not confident at all, 10 sitting there, you're thinking, yep, I could do this morning with a blindfold and I would still get as the high score as possible. So love to hear a bit of input. Mine at this point, when you're in year 12, a couple months out from the exam, how are you feeling?
I remember feeling like really nervous, especially like time flies within this time. And I'm like sitting there like 3 months away, and then in a flick, it's like 10 days. Yeah, it was pretty scary. And yeah.
Yeah, definitely. Flashbacks. And what did you do to help alleviate that stress?
I just did a lot of past exams, ensuring that and I did some meditations that I was told to do it, but it helps.
Awesome. So I'm seeing right now the distribution of everyone's confidence levels, and we're sitting at about a 4.3 average. So, a lot of people, some people feeling very confident, some people not whatsoever, but I think most people are sitting around that middle or lower middle range, and that's completely fine. I know I was sitting out a couple months from my exams, absolutely terrified. All I could think about was, what happens if this comes up on the exam, or this one or this one? I'm doing practical exams and I'm not getting anything right. Like I'm not getting the marks I want to. And I'm going to talk a little bit about this a bit later, but I developed some strategies personally that help me with my chemistry and a lot of my other subjects that really helps alleviate stress. So I want to say, just to begin with, focus on the now, not the future, and let's smash this out today, see how much we learn, see how much we do, and hopefully by the end we're feeling a bit better. Awesome. Fantastic. So let's jump in today. Before we jump in, we do have a question on the Q&A, which will be open at all times. Will the slides be available? Yes, they will be, and the recordings as well. I think we'll discuss that a bit more at the end. So, energy production. All right, so we start off with a bit of the basics. Fuels, simple as that. Fossil fuels and biofuels. Fossil fuels are essentially, is a bit of an overview, and I'm not going to go into too much detail, but oil, gas, coal, and they're hydrocarbons, right? They're the remnants of organic material. So dinosaurs, or almost more commonly just plant matter that over millions of years has been compressed. And that's become our hydrocarbons, our methane, our ethane, our whatever, our benzene, all these different hydrocarbon molecules. So in power plants, what we do is we burn these fuels. And what that does is that that heat will then boil water, and the water and the steam, or the steam produced and the gases produced, and also the boiling of the water will then spin a turbine. And that spinning of a turbine generates electricity. And that produces, our energy. Issue with fossil fuels is that the key things to remember for VCE, because they'll often ask questions like this if it ever comes up, contributes to acid rain, the greenhouse effects, desulfurization, and increased ozone levels. We compare that to biofuels, which is biomass, bioethanol, biodiesel. And these are often considered carbon neutral. Now, a carbon neutral fuel is a very interesting concept. Right? Like, we're burning a fuel. What's going on there? Because these fuels are derived from organic matter existing now, with a bioethanol from crops that we then convert to ethanol. We say that the crops, when the crops are growing, they consume enough carbon dioxide to off-put any carbon dioxide produced by the combustions of those fuels. And they're renewable and relatively cheap. I think we'll move on to the next slide. But the thing I'll flag briefly before we jump into that is that the question I commonly see is, what are the negatives of biofuels? And a lot of VC students, they're like, oh gosh, I actually can't remember. A big one here, just to remember, just if ever comes up in an exam, is you have to use land to grow these fuels. Makes sense, but often the use of that land pushes out agricultural industries for food. So sometimes there's that question of, do we use this land to grow crops to eat, or do we use it to grow crops for energy? So biomass is essentially, or biogas is a combustion of organic material like woods or crops, whereas biomass is it's a mass undergoing chemical reactions to become various combustible gases or ethanol, which is anaerobic fermentation. Bioethanol is another cool one, and it's essentially sugar from crops is converted to carbon dioxide and ethanol, and it burns very cleanly, is more biodegradable than biodiesel, but is hygroscopic, and its production is actually quite inefficient. Then we get to the big one that everyone should know and will always come up on an exam: biodiesel. So vegetables and animal fats, triglycerides, are reacting with alcohol to produce glycerol and a biodiesel. So the fatty acids, and we'll cover this in a while at the end of the section. So the triglycerides usually produce glycerol and 3 fatty acids. Here, when we react it with methanol, typically we'll produce a biodiesel instead of a plain old fatty acid. And you can see there's an ester function group in the biodiesel molecule, which is very different from petrodiesel, which is also a long carbon chain, but with no oxygens included. So the ester link means that biodiesel requires more energy to break the bonds between adjacent molecules than petrodiesel. So biodiesel is great for combustion, but the issue is there's stronger intermolecular bonds, which means it's going to be hygroscopic, going to attract water, but it's also going to be very viscous. It's going to be much more like honey than it would be like water in terms of its flow, which means the classic example is in very cold environments, it's going to freeze. It's going to get stuck in the fuel lines. And likewise, the water that it might be bonded to will also freeze. Awesome stuff. So the big thing, however, in this area of study is activation energy. So I've got a quick question here that would just be great for everyone to quickly attempt. Grab a piece of paper, jot it down. But essentially, we have a reaction here. Nitrous oxide gas plus chlorine gas becomes NOCl, 2NOCl. And our change in enthalpy is negative 38 kilojoules per mole. The activation energy is 62 kilojoules per mole. Draw an energy profile diagram labeling both the activation energy and the enthalpy. So give that one a quick go. Alrighty, wonderful. Hopefully we've got a bit of time to attend to this question. Let's have a bit of a think. Okay. VCE Chemistry is more about just being able to, yep, I know the answer. It's about being able to identify various different things. Nan, what are the key things that you can identify in this question?
I would identify the delta H.
Awesome. So, and what is negative? What does that mean?
Negative means it's an exothermic. So my product will be lower than my reactants.
Fantastic. And that's very interesting. And people often, one of the misconceptions people often have is, okay, negative energy, therefore it's it's taking energy from the surroundings. No. Delta H, or the enthalpy, is a measure of the energy inside the physical bonds in these molecules. So here we start off with a lot of energy. Now, energy can't be created or destroyed. It's always existing. So the energy we have in these bonds here and these bonds here, broken, and the bonds broken and reformed, and the energy inside of these bonds is 38 less than what we start with, which means there's 38 kilojoules just out in the environment now. So we've produced lots of energy. Now, activation energy. Nan, what can you tell me about activation energy?
Activation energy is the minimum of energy required to proceed the reaction forward. Great. And so what this looks like on this graph is a little bump like this. Now, this isn't very much to scale, but we hopefully now we'll do our 2NO plus Cl2. And then we have our 2NoCl. This here is our delta H. And this here is our activation energy, or I like to call it EA, but there's various ways we can put that. Fantastic. And we'd also have to write, equals negative 38 kilojoules per mole, and then activation energy equals 62 kilojoules per mole. Fantastic. So, awesome stuff. Alrighty, and anyone feel free to put questions into the Mentimeter and we'll answer them as we go along. A couple of questions have come up, have been, will we go into further detail about formation of biodiesels? Yes, we will, do not stress. And enthalpy change and heat of combustion. Do exothermic reactions have a negative value in both of these? So the heat of combustion enthalpy change are a little different. I think I've got a question coming up, so I'll address that then. And then if I don't fully answer the question, we can we'll go through that. Awesome, fantastic. And finally, desulfurization refers to sulfur. My understanding is sulfur. The key word is just desulfurization, but sulfur leaving soil. So here's our classic question that comes up. It's found that burning 0.427 litres of butane at SLC causes the temperature of 450 grams of water to increase by 26.34 degrees Celsius. A lot of very finicky numbers, and I do apologise. Using this information, find the enthalpy change for the following equation. Butane plus oxygen becomes CO2 and H2O. Alrighty. This is a classics question that's just testing the stoichiometry. There's a reason why your teacher last year would have stressed stoichiometry, is because it is critical with VCE, and these questions will always be about testing, or the aim is to test your skills at stoichiometry. So we're going to give this one a bit of a go, and fantastic. Another question, sorry, regarding that last slide regarding the enthalpy change diagram is, yes, you could. So the question is, could you start the reaction at 38 and finish at 0? Yes, as long as there's a relative difference of 38 between our start and end point, you're fine. Awesome. But give this one a go. So we've got the key things here are, let's try to figure out what we need to find out. Let's try and find out the number of moles of butane potentially, how
how much energy is required for that water, etc., etc. So give that a go. Awesome. So gave everyone a little bit of time there. Fantastic. So what are we what are we being asked to find? And I think that's the key things here. We have all of our information and that's fine, but we've really got to make sure we're answering the question. And here they're asking the enthalpy change for the following equation. Okay, cool. A couple of key bits of information there. Enthalpy change. Well, enthalpy change or change enthalpy is kilojoules per mole. So we need to find the energy release, but also the moles of butane. Now we're going to use our trusted formula, Q equals MC delta T. Energy equals mass of water times by, or mass of a liquid times by its specific heat factor times by the change in temperature. For water, that's 4.18. So 4.18 times 450 grams times by 26.34 degrees Celsius is going to give us 49,545.5 joules. The reason why it's joules is because I've used grams in the equation. If I use kilograms, so do 0.45, I'll get kilojoules, but either way I can just convert. This gives us 49.5 kilojoules. All right, so I know there's been 49.5 kilojoules put into that water. I also know that a number of moles of butane, I can calculate the formula PV equals nRT. So N, number of moles, equals PV divided by RT. And very fortunately, we have the temperature has been given at SLC. So SLC, so 100 kilopascals times by the volume of 0.427 as given, divided by the factor of 8.31, temperature of 298 Kelvin, which is SLC, standard laboratory conditions, which should give us 0.01724 mole. So our change in enthalpy is the energy divided by the number of moles. So simply 49.5 kilojoules divided by 0.017. It gives us 2,874 kilojoules per mole, and that's negative because it's an exothermic reaction. It's combustion. There's a question about do we have to times density with the mass of water. Here we're using mass, and it was in the question that the keyword was mass there as well. So we have mass to begin with. The issue is, however, if we have a look at this equation here, if I was to put in delta H equals this value here, I would get it wrong because 1 mole of butane produces that much energy. In the equation, we have 2 moles. So we start off with 2, and therefore we must double the available amount of energy. Double the change in enthalpy, because this is a ratio. So it's saying 2,874 kilojoules for every 1 mole, or likewise 5,748 kilojoules for every 2 moles of butane. That is the ratio. That's the classic stitch-up that VC students make, that they don't read the question and it's for that specific equation. Therefore, the delta H will be negative 5,748 kilojoules per mole. One of the other questions was, instead of using PV equals nRT, could you also use N equals V divided by Vn, where Vm is the volume of a gas at SLC? Yes, you definitely could. I just use this as an example. There's many ways to do these questions. I'm just going to show you one, but you definitely could do that as long as you get the same answer. Fantastic. Alrighty, we now jump away a bit from enthalpy change and jump into one of the more critical things, which is galvanic cells. Oh, everyone's favorite. Nan, what did you think of galvanic cells in VCE?
I think it was like confusing to understand at first, but once you understand what's going on, it's pretty interesting and fun topic to do.
Yeah, awesome. Fantastic. So the electrochemical series, I guess, is the key thing, besides from redox. I'm not going to cover too much on redox because I'm confident that we have a good understanding because it's covered in 1, 2, and 3, 4, and there's no point going over some of these things. Let's go over the more complicated stuff. So the electrochemical series is a very interesting series. It's a series of reactions listed essentially in an order of reactivity. So this was calculated by contacting different elements and seeing if they reacted with the energy different from hydrogen used as a baseline. The hydrogen, so that reaction there in the middle, so 2 protons plus 2 electrons becomes 1 mole of hydrogen gas, was used as our baseline factor. And comparing that we gave it an arbitrary value of 0, and we compared all these other half equations to hydrogen to see how it reacted. Strongest oxidants on the top left and the strongest reductants in the bottom left. As we know, the strongest reductant, a reaction will occur spontaneously if the strongest oxidant is above the strongest reductant. So if we have our strongest oxidant up here and our strongest reductant down here, we have I think of it as a slide, and a slide is very easy to go down. So it happens spontaneously. However, if we have, say, our strongest oxidant up here, down there, and our strongest reductant over here, I imagine this is more like a staircase, and it takes a while to climb up a staircase and it takes energy to climb up a staircase. Therefore, we need to put energy in, therefore it's not a spontaneous reaction. But this also only indicates reactions that have the potential to occur. And a critical thing in VCE chemistry is that we're not just applying theory, we're applying practicality. And just because something happens on the electrochemical series doesn't mean it will actually happen in real life. This is for a variety of reasons. One is the electrochemical series requires 25 degrees Celsius to work. And it also requires our solutions to be of 1 molarity and a certain pH. So if a reaction doesn't happen, it doesn't mean the electrochemical series is wrong. It might be it's changed that temperature. But again, the ECS only indicates what reactions have the potential to occur. Reactants with a positive electrode potential are said to be spontaneous and will react when reactants are in presence of one another. So if we have, for example, chlorine gas with lead, those 2 things should react with one another when they're put together. And it requires no energy to be put into a system. But separating the reactants physically into 2 different beakers, for example, you've got to remember that redox is a transfer of electrons. So when we put the lead and the chlorine gas together, for example, what's happening is in between these atoms, there's electrons are moving, and that's what's producing this energy, producing heat. If we move these reactants away so they can't physically contact each other, and then somehow connect them with a wire, the electrons will still be transferred. They'll be moved up and along a wire, which essentially produces electricity. So it allows electron transfer to occur via distance. So reactions with a negative value are not spontaneous, and the system requires energy to be put in for a reaction to take place. So the thing to note is that if a forward reaction is spontaneous, the reverse reaction is not. Fantastic. So galvanic cells, the every VCE student's worst nightmare. So what are the key principles of galvanic cells? Okay, cool. We have our cathode and our anode. Now I have a little mnemonic, which I think is quite useful. An ox. So I think of an ox, like an oxen, and then a red cat. So oxidation occurs at the anode and reduction occurs at the cathode. So a red cat and an ox. So here at our anode, we're going to be having our oxidation. And if you remember our mnemonic oil rig, oxidation is loss, reduction is gain. Oxidation is the loss of electrons, so it gives out electrons. So from our anode, we are therefore going to be moving our electrons outwards. For those of you who studied physics, we know the current goes the other way, but that's fine. We don't need to worry about that. But our electrons are moving from the anode to the cathode. Likewise, we have our electrolyte here. An electrolyte is essentially a solution that's so typically these cells should be properly divided, but electrolyte is the other solution that allows us to undergo these reactions. So we've got two different reactions in place. The thing to note that I'm going to briefly explain is the concept of the salt bridge, and a lot of people don't actually understand what the salt bridge is. So we call the wire that connects the two half cells the external circuit, and the salt bridge is called the internal circuit. So we've got to note that the anode is negative. The anode is a negatively charged electrode. Anode is negative, like anion, and electrons move away from it into the external circuit. Where the cathode is positive, and obviously the cathode is where the reduction occurs, so it needs the electrons, so the electrons move towards there. And in the oxidation half cell, essentially what's happening is we're undergoing oxidation, so we're producing those electrons, but we're also producing cations in a metal. If we're using metals, we're producing cations. And so there's cations that are accumulating, which would increase the charge of the cell. And you've got to remember this happens in the anode, which is negative. But accumulating this charge makes it positive, which means everything will immediately stop because the electrons will want to leave one way, but they can't because they're being drawn back by the positive charge. Likewise, on the other side, we're losing in our cathode, we've got our positive ions in the solution, and we're losing that positivity. So it's not becoming negative, it's just becoming less positive because our positive ions are going into the electrode and becoming metal. And what this means is the positivity, if we measure it, is decreasing. But essentially, we use a salt bridge or the internal circuit. And the salt bridge contains an unreactive iron salt, like potassium hydroxide or something like that, or potassium nitrate, I think, is the best one to use. And essentially, like anions will move to the anode because we're getting all these positive charges in the anode. So we're going to move our nitrate, for example, into the anode, which helps balance that charge out. Likewise, in the cathode, we're losing our cations to become the actual metal, become the solid in the electrode. Cations from the salt bridge will move in, which will then balance out the loss of that charge. So the electrolyte at the salt bridge must be able to conduct electricity, but also not be able to interfere with the reactions occurring in each half cell. So we couldn't put something like, I think it'd be pretty weird to put chlorine in there because chlorine can properly interfere. But potassium nitrate is most commonly used. So I've got a quick question here, and it would be great if people pop into chat. Pop into chat what you reckon the answer might be. Awesome. So we've got two standard galvanic cells that are shown here. We've got one with cadmium and copper and cadmium and this manganese solution with a platinum electrode. On the basis of polarity of the electrodes shown above, which are the following reactions would not be expected to occur spontaneously. So we'll put a bit of music on just for 1 minute. So it's a 1 mark question. Give it a go and see what you think. Sorry, music not quite as upbeat as I was expecting that one to be. Apologies. Alrighty. Does anyone have, what do you saw this question in the exam, it's a tough question. What do you reckon, what do you reckon you do? What things would you highlight maybe?
I highlight the electrodes and
Great.
what reagent is associated to each electrode and compare it with the electrochemical theory in the data booklet.
Great, fantastic. So the thing we know is that we can't necessarily compare to the ECS because we have, we say standard, but let's just work on the information we have with us at the moment. Now, so if we jump in, we know that our positive electrode, a cathode, is where reduction occurs. So we know reduction is occurring. So we're going to have, let's see, CO2 plus, reduction is gain plus 2 electrons, going to become CO. So we know that CO2 plus is going to be a stronger oxidant than CD2 plus. So if I'm going to draw this up, I know CO2 plus on an electrochemical series, on the one we're making right now, is greater than CD2 plus. Because what's happening is we have CO2 plus here, the cathode, becoming our cobalt. And so this is essentially growing, whereas here our cadmium is, we're depleting our cadmium electrode at the anode here, because that's negative. So electron flow is this way. Likewise, on this side, our electron flow is this way, which means our manganese, our permanganate, sorry, not our permanganate, our manganese is flowing. And the equation here would be Mn3 plus. Remember, we're gaining the electron. So this is a classic switch up here. Nm3 plus 1 electron will become Mn2 plus. So therefore, on our series, we're going to have Mn3 plus above. Now, these are two aqueous reactants. Therefore, we're going to be using a platinum electrode. So the classic switch up here is thinking, oh, cool, platinum's one of our reactants. No, platinum is inert, which means it doesn't react, and the electrode provides a place for the reaction to occur. Absolutely fantastic. So what would we expect? Let's go through. The first one, cobalt plus cadmium becomes cobalt solid plus cadmium ions. Well, that's, as a matter of fact, exactly what's happening here. So we can mark this one off. Here, Mm3 plus cobalt, well, yeah, potentially becomes Mm2 plus cobalt 2. Unlikely. Let's just move to the next one. Well, in fact, that's the opposite of what's occurring here, I believe. Finally, sorry, not finally, we have 2 Mf3 plus cadmium metal. Well, again, our cadmium becoming this. So, which would not be expected to occur spontaneously. So we know that these three are what's happening already. Or this one here is what's happening up there. This one here is what's happening there. And this one here is just makes sense because it's just the mixture of the two. This final one here, Mn2 plus copper, cobalt 2 plus, means we're going to be going backwards at the top and then forwards here. So this is the one that won't actually actually be able to take place without us putting energy in. Fantastic. So I've got a quick question here. I won't spend too long on this. Pretty basic question, but one that they always like to throw in. A solution of nickel chloride and copper chloride are poured into half cells containing a strip of nickel and a strip of copper, respectively. A salt bridge and a set of wires for the voltmeter are used to connect the two cells. Write the overall equation, draw the galvanic cell with no annotations, describe the function of the salt bridge, and calculate the voltage expected to be seen under standard conditions. Awesome. Okay, give that one a go quite briefly and see what you think. Awesome stuff. So I didn't give everyone a lot of time there, so I do apologize. But let's jump in and just go through a few of these things. Okay. So write the overall equation that occurs. So what I like to do personally is I like to highlight everything that I have. So I know I've got two aqueous solutions. I've got an aqueous copper and aqueous, these aqueous solutions. So I'm going to circle aqueous, well, water's there. We have water, so circle our waters. We've got our nickel there with nickel solid and nickel solution, and copper solid and copper solution. So our strongest oxidant is going to be our copper, and our strongest reductant is going to be our nickel solid. Fantastic. And that goes straight down. So that's like a slide, so therefore it's spontaneous. So we have copper 2+ becoming copper solid, or sorry, the format's jumped around there, and nickel solid becoming nickel 2+. Therefore, simple enough, we can add these together. This is very, very simple. To add the two equations together, the electrons cancel out. We have nickel solid plus copper cations becoming nickel cations and copper solid. Note the 2+ is because if I just run back, we have 2 in brackets there. So that 2 in those brackets means it's got 2+. Fantastic. Do the galvanic cell with annotations. Now I've done a very poorly drawn galvanic cell, but I hope to emulate what it might look like on pen and paper. We've got an anode with nickel becoming nickel 2+ and electrons, a cathode with the copper, our external circuit, and make sure to draw the voltmeter in because that's provided in the question with our salt bridge. Awesome. So describe this function of the salt bridge. Now, as we went over previously, the salt bridge contains a conductive ionic salt. As oxidation reaction produces more nickel 2 ions, the charge in the half cell increases. Likewise, the reduction at the cathode results from the change in the half cell decrease, the charge in the half cell decreasing due to the copper 2 ions being reacted. Cations of the ionic salt migrate to the cathode and anions migrate to the anode, which stops accumulation of charge. And the voltage is very simply going to be, if we see here, +34 minus -0.25, which gives us 0.59 volts. Fantastic. So the other types of cells we have are fuel cells and electrolytic/secondary cells. Now I'm going to talk about electrolytic cells in the context now instead of waiting till area study 2 because it just makes more sense in my opinion. But no, this isn't part of the same study design. So non-fuel cells. Sorry to grab you while you're taking a drink. What's different about them? What's cool about them?
Fuel cells.
Yeah.
It's cool that you can just provide it unlimited reactants, and it go on forever, and it's better than galvanic because of that aspect, I guess.
Yeah, fantastic. So I think the thing I like to note here is we talked a bit about earlier with combustion reaction. What's happening is essentially in a power plant is we combust our fuels. So the energy in the bonds is converted to heat energy, which heats up water, which is energy converted to kinetic energy, which is then converted to kinetic energy and turning the turbines around, which is then converted to electrical energy. So there's a lot of transfers there and a lot of loss. Fuel cells are like a galvanic cell, but we combust these fuels almost separately and we use the transfer of electrons, which means we're jumping straight from bond energy to electrical energy, which is super efficient. And as I was saying, like they can just go on forever and ever as long as we're providing all of the reactants and getting rid of all the products. And a continuous electrical supply is produced and it doesn't need recharging, unlike secondary cells. They're really good. The issue is, when it comes to how feasible is this having a fuel cell in your car if you've got to have, 100 liters of ethanol or 100 liters of compressed hydrogen gas in your boot. And you can imagine something like that, compressed hydrogen gas, you get into a crash, it's going to be very, very devastating. So that's a big key thing, is that the feasibility isn't great right now. We also have electrolytic or secondary cells. So electrolytic cells produces non-spontaneous reactions by passing a current through the electrolyte. And the potential difference of the battery is greater than the potential difference generated by the reverse spontaneous reaction. So essentially, let's say we have a reverse spontaneous reaction that produces 1 volt of 1 volt. The battery needs to put in order to charge this reaction to make it the reverse occur, needs to be more than that. And a thing to note is here, anode is still where oxidation occurs, and the cathode is where reduction occurs. Sorry, I lost the word for a second there. But in this case, the cathode has negative polarity and the anode has positive. And the thing that VCE students always mistake is that we've got a battery here, positive and negative. Positive and negative. Here we have the cathode, and our cathode is negative. Anode is positive. So positive attaches positive, negative attaches negative, because our electrons are going to flow this way into the negative electrode or the cathode, because that's where reduction is occurring. Fantastic. So, got a brief question here, and I reckon we just try to give this one a go. So a new type of fuel cell is developed. It's operated by oxidizing H2S, gaseous, to sulfur using oxygen gas. Write the half equations that occur at the anode and cathode in an acidic environment. I'll go through this. Given that 1 mole of H2S releases 925 kilojoules of energy, write the thermochemical equation for the reaction that takes place. Explain the use of porous electrodes in this fuel cell. A student studying this cell in class states the fuel cell will work as no salt bridge is present. Discuss. And finally, scientists review the original half equations in an acidic environment and decides that an alkaline environment would better suit the cell. Write out the half equations for this scenario. A couple of tricky ones here. The thing I would like to note is, if I just move forward, so we just start off with the first 2 questions. Write out the half equations. We are just going to be, just for knowledge here, H2S is our reactant, and we're producing sulfur, which is just S. So this here's a question about balancing. You have the equations here. Balance those, and it's oxidizing. And remember, oxygen gas is also being used. So start off with this half equation, give it a brief go, see how you feel, and then give that second question and we'll go through the rest. Wonderful. Hopefully that question is a bit challenging. It's meant to be, so don't feel too stressed, but we'll go over. Just to address a couple of questions that were raised up in the Mentimeter. Appropriate salt bridge. Okay, I would always just say KNO3. I think essentially you're going to be looking for something that isn't reactive. You know, you start putting hydroxides in there. Well, no, that's going to mess up your equations. You start putting, you know, too many different of these anions are going to be quite complicated. I would always say some sort of nitrate, personally. Sodium's often a good one because that often won't mess up the equation. But again, like I think potassium nitrate is probably the best one to be using. People also comment on the differences between fuel cells and galvanic cells, and the biggest difference is that galvanic cells, you know, you have your reactants there, whereas fuel cells, you require this constant input of reactants and constant export of products. Alrighty, let's jump into this answer. So write the half equations that occur. Okay, so here's our answer. You might be like, Josh, how did you do that? We know we've got H2S, and we know we're going to be producing sulfur gas. We can use our principle cohes, key elements, oxygen, hydrogen, electrons, and states. So we first balance our key elements, one sulfur on either side, it's fine. Oxygens, there's none. Hydrogens, we just add our 2H+, and then finally we finish off with our electrons, which we add there. For our oxygen, this is just on the chemical series, and this is just something you'll come across in lots of fuel cells, that this equation is always going to be used. 4 electrons plus oxygen plus 4 hydrogen ions becomes 2 waters. Those are the half equations. Now this next question is almost like a 2-step process. There's quite a few different things you need to do. Also, yeah, one for the anode, one for the cathode. So first thing is first, the issue here is we can't just add these together because we've got 2 electrons on this side and 4 electrons on this side. So if we're going to try add them, Joe, make the full equation, we're going to have to double everything here by 2. So we're going to have 2 H2S becomes 2 sulfur plus 2 4H plus, 4H plus, which gives us here 2 H2S plus O2 becomes 2H2O plus 2S because these 4H and 4H will cancel. So that there is the first step, and that's going to be our first easy mark. Next thing we know is we know 1 mole of H2S releases 925 kilojoules of energy. Now, the thing we know from the question earlier about butane is that this equation here, the thermochemical equation, is going to require double because the thermochemical equation, the equation has 2 moles of H2S. Therefore, if 1 mole of H2S produces 925, 2 moles to produce 1,850 kilojoules of energy. So therefore, our delta H will be negative 1,850 kilojoules per mole. So again, always relates a ratio based on the coefficients in the actual equation. All right, explain the use of porous electrodes in this fuel cell. This fuel cell uses porous electrodes. Porous, you know, having lots of holes in it, like Swiss cheese. That's how I like to remember it. Well, 1, it increases the surface area. You know, if you've got a larger surface area, you're going to increase the rate of reaction, which means it's going to be much more efficient. But it also allows for the passage of ions between different compartments. So, and then a student in the class studying class states this fuel cell won't work. There's no salt bridge. Well, what do we have to say about that? These discussed questions will be like, well, no, they're wrong, because the membrane acts as a salt bridge in a fuel cell, the membrane between the compartments. And finally, scientists review the original half equations in an acidic environment and decide an alkaline environment would better suit the cell. Write up the half equations. So here I have the half equation from the original acidic environment, and I'm going to go through and discuss these. This is often a question that people don't get. They haven't talked about alkaline environments, like what, acidic? But cohes only works in acidic environment. Like cohes is used in acidic environments because the H is hydrogen ions. Remember, this is acid essentially. So for an alkaline environment, well, what do? It's actually quite simple. We do the exact same thing, exact same process, we've got same balancing, but we add hydroxide. So here we are going to add, well, we've got 2H plus, so we're going to add 2 hydroxide to either side, 2OH, 2OH. And likewise, we'll do 4 down the bottom. And our 2H plus and the 2OH is going to become water. So in fact, we're going to get 2OH negative plus H2S becomes sulfur plus 2 lots of waters and our 2 electrons. And we can see that here, even though there's a negative charge on the left now, our charges are still balanced, 2 negatives on either side. Likewise, if you do the same over here, we are going to get, we add our 4 OH on either side, so we're going to get 4 electrons plus oxygen gas plus, now 4H plus 4OH is going to give us 4 waters, so 4H2O. Remember, like, but Josh, there's water on the left-hand side. Yes, so that will cancel out from both sides, which means we've got 4 on the left, 2 on the right. So that means we're going to have 2 waters here. And that's going to become, we added 4OH on the left, so we're going to add 4OH on the right. So it's going to be 4OH negative. And as you can see, there's still, even though there's now a charge on the right-hand side, there's still an equal charge on either side. So simply making an alkaline is just adding OH to either side. Easy enough. Awesome. So Faraday's laws. Oh, these are interesting. So essentially, over a period of time, scientists noticed that during electrolytic cells, where they were trying to do they put energy or electricity into the cells and then see what happened. And they noticed that if they increased the charge, the amount of metal they produced would increase. And likewise, the charge could be increased by increasing amperage or increasing the amount of time a system could run for. Therefore, if charge increases with amperage and time, and charge increases metal produced, time increases metal, and amperage increases metal. They also noticed that ions with a higher charge would produce less solid metal. So compared to, say lead 4 plus, with 1 mole of lead 4 plus would produce, 10 grams of lead 4 plus would produce less metal per se than with the same charge than other ions. So essentially, they came up with a few equations to try to explain this. Our first one is Q equals Ne times by F. So essentially, this is a bit weird, but essentially, they've used this F, which is a constant. And we're going to know a constant is essentially, in this sense, it just refers to the total charge on 1 mole of electrons. So remember, Avogadro's number of electrons, which is 96,500 coulombs. C for coulombs, which is measured here with Q. That is not energy. So our rule 1 is that the mass produced or consumed at an electrode is directly proportional to total charge passed through a system. So you increase charge, you increase the mass produced or consumed, or you decrease charge, you decrease mass produced or consumed. Anything that changes Q will change, or charge will change the amount of substance produced or consumed. So if we change amperage or time, we'll change the charge. Likewise, another fancy formula is E, energy equals voltage times by amperage times by time. Rule 2 is that the mass deposited or consumed electrolytes is inversely proportional to the charge carried by equivalent metal ions. For example, iron 3 ions will produce less metal iron than iron 2 ions with the same amount of energy in the system. And that's just because we require 3 electrons for every 1 ion here to create 1 molecule of iron metal, whereas here we only require 2. And because the charge is linked to the number of electrons, we're going to require the same amount of charge is going to produce less, or rather to get the same amount of electrons will be the same charge, but to get the same amount of product, because this has got 1.5 times more reactant, we're going to need to increase the charge. Alrighty, amazing stuff. So secondary cells. Whilst a primary cell can be used once as a galvanic cell, a secondary cells can be used multiple times. And this is essentially a rechargeable cell. In primary cells, products drift away from the electrodes and accumulate or are consumed by accessory reactions. But in secondary cells, the products of a reaction are converted back into their original reactants. So we undergo it's like your phone, essentially. You've got a battery and it's like processing galvanic cells to produce energy. You plug it back in, and essentially inside those cells, we're providing the energy or the charge to go back, essentially reassembles our electrodes, for example, and this process is recharging. That's a secondary cell, rechargeable battery. So I've got a quick question here that we'll go over. We won't spend too much time on it. But we have essentially a zinc cerium battery is a commercial rechargeable battery that comprises of a series of cells. During recharging, the cells use energy from a wind farm or solar cell panels. During discharging, energy is supplied to electric grids to local factories and homes. The electrodes are stored in 2 separate storage tanks and are pumped into and out of each cell when in use. The membrane here, and this answers a question that was raised earlier about the membrane, is immersed in 1 molar methylsulfonic acid or CH3SO3H. And this is the zinc cerium cell. So essentially we have zinc with sulfonic acid. So here we've used the membrane in the equation here. So zinc has got two positive charge, and this ion here without the hydrogen has got -1. So here we've got 2 of them attached. So this is used in the full equation. So the zinc ions, so we've got to look at this. This is ionic. So this is all that it's saying is Zn2+. And this is when, sure, we can start using the electrolyte in the equations, but really this is counterproductive. You don't actually need to include it. But anyhow, that will become zinc solid plus. In this sense, we would include it because that's one of our products. And likewise, we have our cerium there as well. And here we've got the 4+ going down to the 3+. So write the equation for the overall discharge and determine the theoretical voltage. So the highest E value is a reduction reaction in discharge. So what they've done is that they've been a bit tricky, and in the electrochemical series, this bottom one would actually be on top, which means we're going to have the 2 cesium, and I've doubled it because we've got only 1 electron. We need to double it for the 2. The 2 cesium plus 2 hydrogen ions plus 2 electrons plus zinc plus our methylsulfonic acid. So I've taken, what have I done? I've taken, got our green here, right? Because we're going to go forward in this reaction and backwards in this reaction. Here are our products and here are our products. And that's going to produce our reactants. Sorry, those were our reactants, apologies. And that's going to produce our products here, here. A little bit confusing. But that's going to produce our, if we look, our 2CeCH3SO3 plus our 2CH3, our 2 methylsulfonic acid, plus our zinc with the methylsulfone ions and our 2H plus the 2 electrons. Cool, we can now cancel stuff out. 2H plus and 2E cancel out. Luckily, our methylsulfonic acid also cancels out, which gives us 2 cerium plus zinc solid plus our 2 cerium 3+ and our zinc ions. Or more simply, because, apologies. I'll just share this again. Now, can you still see my screen? Is that good?
Yes, it's all good.
Awesome. Fantastic. Essentially, because these are all the same ions, really, so it doesn't matter, they aren't like CH3SO3, it's no different to having like Cl minus, essentially. So really, we can get rid of all of these, which gives us 2 cerium 4+ plus zinc becomes cerium 3+ plus zinc 2+. And remember, I've got to include my states: aqueous, solid, aqueous, aqueous. Awesome stuff. So I'm just going to check our Mentimeter. Awesome. Okay. So we're now going to have, we've been going for an hour, we're now going to have a quick break, but before we do, we've just got the question I forgot to answer here. Theoretical voltage produced by a single cell as it discharges. We have 1.64 minus -0.76 gives us 2.4 volts. And our final question is about secondary cells. We have write the ionic equation reaction occurring at the positive electrode during recharging. Well, a positive electrode during recharging is the anode. So it goes from negative to positive. Therefore, the oxidation reaction occurs, which in electrolysis is the backwards reaction of the highest E, because we're going to in our forwards we're going to go here and here, but in recharging we're going to go this way and this way. So it's simply going to be, right, the ionic equation, it's going to be, well, here it's writing out exactly what it has, but our ionic equation doesn't include our CH3s. So it will simply just be our Ce3 plus our Ce3 plus becomes Ce4 plus an electron. Other than transporting ions between the electrodes, describe one function of the membrane. The membrane acts as a salt bridge. That's already been indicated in the question. But what it does, it prevents the oxidant reduction from coming into direct contact, which prevents spontaneous reactions and prevents the release of thermal energy into the cell. Now, I'm just going to clear my annotations and we're going to watch a brief video from our sponsors at UBS.
Hi, my name's Emma. I work on the equity sales desk at UBS, focusing on hedge funds. My biggest career highlight to date was hosting a panel with over 150 clients who were based around the globe with one of my colleagues a few weeks ago, presenting on one of my pieces of work. At university, I studied commerce with a focus on French, data science, and finance. And in high school, French was one of my favorite subjects. Advice to my younger self would be to make the most of your youth and just ask as many questions as possible, really leveraging the fact that you don't need to know all the answers. All the best with your studies.
Absolutely amazing. So I'm just going to move forward. A fantastic video from the Stress Hack program, which I'll just share. Sorry, I'm just going to stop. Sorry, I think this is just messed up a tiny bit. Sorry, apologies. Here we go.
Something happens when we feel really stressed, like borderline anxious. Something happens in our brain that, unless you know how to deal with it, it's actually one of the places where our brains actually totally hold us back. Like they make things stacks worse than they actually need to be. So in this video, I'm gonna share what actually happens in our brain so that you get what's going on, but then also share something you can do, like a little hack you can do that's super simple that you will always have. Like once you hear it, you'll always have it. You can always use it. That helps you override some of the default stuff that our brain does that literally, gosh, I mean, our brains are amazing, like totally extraordinary. Like, you know, it's hard to believe that in some ways it completely holds us back and has us feel horrible and completely overreact during things like, you know, taking an exam or asking someone out or public speaking or being in an interview. You know how stressed out you can feel about that? And logically you go, that makes no sense, I'm that stressed. Like what's the worst that can happen? But in your body, you're completely freaking out. So when that stuff starts to happen to our bodies, when we're worried about something, it sends a signal to our brain that it needs to protect us. And the problem with this is that the signal it sends is that it needs to physically protect us, like we're in some kind of physical danger. So what it does is it sends a shot of stress hormones like adrenaline to our body that has us get into the mode of being able to either run away or stay and fight. So fight or flight. It gives us fight or flight chemicals because it thinks we're in physical danger. And normally we're not. We're like either really worried that she's gonna say no, or we're like worried that we're gonna fail an exam, or we're not gonna do well in an interview. But we get these stress chemicals that have us like seriously, like we're pumped up. to fight or to run away. And that's the last thing you want to experience in your body when you're just about to do something that has you need to be in your head. Because you actually can't be in your head when you've got those chemicals running through you. They actually shut down your brain. Like your mind wants you to be 100% focused on your body and using it to either run away or stay and fight. So it doesn't want to spend any energy in your brain thinking through things. Like, that's the last place it wants you to spend energy. So you literally, like, you can fully go blank or just forget stuff and go, what happened to me there? So here's what you do. You simply have to say something to communicate to your brain why you're feeling stressed. It sounds corny, but you have to say, you're okay, Leah, you're gonna be fine. You're just stressed because this is really important to you. You are safe.
Wonderful. Leah works for Skyline and is such an inspiration. She has such incredible ideas and is really, really helpful. And I think now more than ever, in these hectic times, but also coming up to exams, understanding your stress and understanding how to deal with stress is particularly important, because we mustn't let it overwhelm us. There's lots of important things for us all to do, and let's focus on those. Fantastic. So next big thing, yield and equilibrium. Not as big as a previous section, obviously, because we moved electrolysis into that section, so it's not too bad. Collision theory is the first big thing so we have to understand. Collision theory is essentially the theory that states that molecules they're always bouncing around in the air, right? And in order for a reaction to occur, they must hit each other or collide with enough force, but also the correct orientation. So we can see here in this top image, we have our carbon dioxide on our NO3, and the carbon hits nitrogen, and they're quite slow. Here we've got enough energy in the second one, but it's facing the wrong way. So it actually requires a very specific orientation for a reaction to occur. But if they're energetic and correctly oriented, they will react and form from a carbon monoxide to a carbon dioxide. So when colliding, some of the kinetic energy becomes vibrational energy in the vibrations of the bonds, and the reaction only occurs when the vibrational energy is greater than the activation energy, essentially the energy required to break bonds. So only a small proportion of collisions result in a reaction, essentially. So they have to have enough energy and collide in the right way. So therefore, to increase the rate of reaction, we can either increase the number of collisions total or increase the proportion of those collisions that are successful. So to increase the frequency of collisions, we can concentrate a solution. But to increase success, theoretically, we could have more molecules in the correct orientation, but that's not possible. But we could more simply increase the energy of the particles. So essentially, increasing surface area, what's going to happen is more reacting particles come into contact, which increases number of collisions. And then we go through this process here. Increases the number of successful collisions, increase the number of bonds broken, which therefore increases the rate of reaction. Increasing the concentration or decreasing volume means particles collide more commonly, increasing number of collisions, therefore increasing number of successful collisions, total number of successful collisions. Increasing number of bonds broken, increasing rate of reaction. Temperature, probability of a collision increases with speed, sure, because the higher temperature, the faster they are, it's more kinetic energy. But the main thing is particles collide with more energy, which increases the proportion of collisions that are successful, increasing number of bonds broken, increasing rate of reaction. A final big one is catalyst. A reaction requires less energy for a collision to be successful. Therefore, the proportion of successful collisions increases, number of bonds broken increases, rate of reaction increases. As we can see here with this graph, just going to grab my pen. So here it is. Okay. So here we've got kinetic energy. So this is the measure of kinetic energy and number of molecules. So in a normal environment, we're going to have some molecules with very little kinetic energy, and then most are going to be, this area tells us the total amount of particles. But as we go down, you can see there's very few particles with a certain energy. And this point here is where our activation energy is. So the molecules colliding, only this proportion or this area, when they collide, are actually going to be able to react, because by far the majority are sitting down over here, which don't have enough energy for the reaction to occur. However, if we add a catalyst, which decreases the activation energy, we can see that now our area is all of this, which isn't that much bigger, but still many times bigger than our original equation, activation energy. Conversely, if we have our red line as T1, we could have increased temperature of T2. And so the area will stay the same. But what happens is if we increase the temperature, we increase the proportion of collisions. So we increase the proportion of particles that have a greater energy, which means that it's almost like we push the graph over to the right. So the same area applies, but it's not as peaked and it's more spread out, which means in our original equation, in our original temperature, we just have this area here. Only these number of particles are going to be able to react with that activation energy. But now it is, if we change the temperature to higher, now it's going to be that entire area that, as we can see, is much, much, much bigger. So that's the two ways essentially it works with the proportion of successful collisions, adding a catalyst or increasing the temperature. Fantastic. So equilibrium is our next big point. And this is reversible reactions. So if there's sufficient energy available, whilst reactants, in some equations, not all equations, but in some equations, whilst reactants are colliding to create products, those same products are colliding at the same time, right? Like things are bumping around. But those products could also hit each other with enough energy in the correct orientation and then undergo the reaction in the other way. So the idea of equilibrium describes a point at which the rate of the forwards reaction equals the rate of the backwards reaction. So both reactions are still happening, but in terms of the net change, there's nothing. So the net concentration of products and reactants don't change. So if our rate of forwards reaction is greater than backwards, a net forwards reaction is occurring because there's more stuff happening in the forwards reaction. Backwards greater than forwards, well, backwards is occurring, but if they equal each other, equilibrium has occurred. So essentially the equilibrium constant, KEQ, or just K, is essentially a calculation that expresses the relationship between the concentration of reactants and products at equilibrium. Now it's expressed as, for the equation, an A number of A plus B, so whoops, that's not a B, B becomes C, and I'm sure we all know this, becomes D. So it's the concentration of the products on top to the power of their coefficients divided by concentration of reactants divided by the power of their coefficients. So this essentially just tells us a relationship. It's going to give us a number. It's going to give us a number that describes really what's happening. But as we can see, so this is, and then so equilibrium occurs at a certain number, and that could be of any combination of these. But equilibrium occurs at a certain number for a certain equation. Now Q, this also equals Q, but Q is just a calculation. So if we put all of our data in and then we get Q, if Q is less than K, that means we need more products, so the forward reaction is occurring. And if Q is greater than K, that means a backwards reaction is occurring. And if Q equals K, well then we're at equilibrium. But as you can see here, let's say we've got a K of 20. That's our value, right? And all of a sudden I decrease the number of, I somehow get rid of all of the D in the D molecule in our solution. Now it's going to try to reach K again. It's no longer in equilibrium, but it's going to try to reach that 20 again. So it's going to try increase our D, the D here, which is also going to massively increase the number of C. And it's going to decrease everything down here. Again, it's a mathematical ratio. So it doesn't have to be the exact same as last time. It's going to have all different numbers, but those will again reach that. And that's a big concept a lot of people don't get, is there's not certain numbers of reactants or concentrations of reactants and products that are required. It's just the relationship between them needs to produce a certain number. Awesome. So another big thing that a lot of people don't understand is heterogeneous reactions, which is reactions that involve essentially reactions and products of multiple different states. So the concentration of pure solids or liquids is assigned at 1 molar when we put it into that equation that we did previously. As these concentrations are constant, so they're just 1, we remove them from the equation. So for example, the reversible reaction, calcium carbonate becomes calcium oxide plus CO2. Because we've got the solids there, our equilibrium constant is just CO2. So it's just the equilibrium constant is just the concentration of CO2, which is kind of crazy because we assign this to be the concentration of 1 molar and 1 molar. So dissolution of a solid ion into an aqueous solution, for example, breaking something down, like putting salt into water, is another example where solids aren't calculated. So this brings us to the idea of dynamic equilibrium, where energy can only be exchanged with surroundings and no new matter can be introduced. So reactions such as combustion are irreversible, as we cannot transform CO2 and H2O back into fuel and O2, but other reactions are considered reversible, where some of the products will react with each other to perform the reactions, whilst the original reaction is still taking place. So we have to remember is that if we're going to do a reaction, it's not going to go to its predicted extent. We could calculate it through stoichiometry, but it won't go to its predicted extent because it's going to be having some reverse. Reactants will react in and products will be produced in the molar ratio, which means if we've got 3 moles of, 4 moles of reactant 1 is consumed, and reactant 2 will have 3 moles consumed and 3 moles of total products will be assuming the 1:1:1 molar ratio. Therefore, we can actually predict the extent of reactions and calculate equilibrium constants. This brings us into equilibrium changes, where the position of equilibrium will be changed by alterations to the system. So if the concentration of any compound is disturbed, the system will try and change to re-achieve equilibrium. So for gases, equilibrium also involves a number of particles. If the pressure of the system changes, equilibrium will be re-established in reference to the number of particles. But temperature will change our equilibrium constant, which will therefore change equilibrium. So for example, if I were to have, I have, let's say, 2A plus 1B gas becomes 2C, and let's say our C's are in red, our A's are in pink, and so is our B. We can see here that we got 3 products and 2 products and 3 reactants, and let's say we suddenly have like a piston in here, and the piston pushes down, which increases the pressure, decreases the volume. Well, now we want to try to get back to the original pressure, the system will. So the system is now going to choose the side with the least molecules, which means it's going to actually push the reaction forward, which is going to produce, means we're going to get rid of those ones to try to get less, to try to re-achieve the same pressure. So that's just something to note. So number of particles, we increase the pressure, we're going to favor the side with the least particles. We decrease the pressure, we're going to favor the side with the most because we want to re-establish pressure as well. So here I've got a question. For the reaction 2HI becomes hydrogen gas and iodine gas, 4 moles of reactant was reacted in a 2-liter vessel. When equilibrium was attained, 25% of the HI molecules had dissociated. Find the equilibrium constant. This is a tough question, and that's all you get. Now, I want everyone to try to give it a go. Think about, they're going to react in molar ratio, and 25% of the HI has gone. How are we going to be able to figure out what else is around? Okay, give it a go. We'll spend like a minute or 2 minutes on this, and I'll share some music. Awesome stuff. So before we jump into this question, I've had a couple of questions in the Mentimeter about Q and K. So I'm just going to jump back to here. Okay, so if we were to calculate, so K, we might not necessarily be given Q or K, but let's say we have the concentration of all of our products and reactants, and we put them in. If all of those are at equal, if we're at equilibrium, the value we get from this equation will be K. If we're not at equilibrium, the value we get will be Q. And let's say they give us K, they say K is 20 and we find out that Q is 18. Well, then we need to, Q is less than K, which means we need to increase the top here or decrease the bottom, which means we're going to favor the forward reaction. So Q just indicates where we need to go to get to equilibrium, but it doesn't actually tell us like it's not used at equilibrium. But if they were to say, you know, K is at 30, then and like here's all the concentrations, find Q, and Q is also 30. That means Q equals K, which means the system is at equilibrium. So it just tries to give us an indication of where we're at. It kind of comes up here. Alrighty. So what I like to do here is do something that's called an ICE table. Okay. So let's highlight our key things to begin with. Okay. So we have 4 moles of our reactant, and it's reacting in a 2-liter vessel. And this is critically important because we need to use concentrations. When equilibrium was attained, 25% of the H molecules are dissociated. Okay, so I know I start off with no H2 and no I2, but 4 moles of HI. And only 25% have disappeared by the end. So therefore, 75% is left over. So 3 out of the 4 moles are left over. So ICE, initial, change, equilibrium. I know all of our initials. And I now know the change is going to be -1. Which means if I lose 1 here, this is a 2-to-1 molar ratio. So for every 2 I use up here, I'm going to produce 1 of each of these. So therefore, if I lose 1, well, half is going to go here and the other half is going to go here. So therefore, we're going to increase by +5 in both. Therefore, our equilibrium is going to be 0.5 and 0.5. That's essentially, it's simple as that. That's our ICE table. So find out the change, apply the molar ratio, put the change in for everything, and then you can find out the equilibrium. Now, the issue is where I use moles here. You can use concentration if you want, but I like to do moles and then move to concentration. So concentration equals 2 liters. So concentration is 3 divided by 2 is 1.5 molarity. H2 is 0.25, which should be molar, and 0.25 iodine as well. Now, here I've set up my KEQ. So products on top, H2 and I2, and then HI. And because it's 2 in the equation, I have to square it. Now, the thing to note is that the units in a KEQ are molarity. So I've got molarity here times by molarity, which means our unit's going to be m squared. But I've also got molarity squared down the bottom, which is m squared, which means my unit's going to be m to the 0. But if this wasn't squared, it would be, you know, m times m divided by m, which is just 1m. But in this case, it's just m to the 0. So make sure we're using those units properly. I put all my information in, put it in my calculator, and that gives me KEQ of 0.028 with no unit, or you could write m to the 0. But m to the 0 is just 1. And that there is our equilibrium constant, and it's simply as that. Now, I have another brief question, and I'm just going to see how we're going time-wise. I'm going to run through this one for us. So a student investigates the following reaction, where 2NO2 becomes N2O4 with it's exothermic, where the reactant gas is brown and the product is colorless. The reaction can be observed in a sealed test tube. State the color change expected when the student places the sealed test tube in a beaker of hot water, and explain why this change occurs. Well, as the forward reaction is exothermic, the backwards reaction is favored at high temperatures. You might be like, why? The way I like to think about it is a forwards reaction is producing heat, right? That's meant to be my interpretation of fire. And our backwards reaction is absorbing that. So I'm just going to draw like a snowflake. You can see I lecture chemistry and not art. But anyhow, so if we increase the temperature, the way I like to think about it is, well, we want to try get back to the original system. So we want to try cool the system down, which means we're going to go backwards. If the reaction was endothermic and we increase the temperature, Therefore, we're going to try endothermic. It's going to absorb. So likewise. So that's the way I try to remember that. But essentially, as the forward reaction is exothermic, the backward reaction is favoured when we increase the temperature. Therefore, our NO2 increases and the equilibrium mixture is darker. Hence, the colour changes to a darker shade of brown. Simple as that. So we've got another question here where we have 2 NO2, or it continued, sorry, 2 NO2 becomes our N2O4. And the graph below describes the concentration versus time at 22 degrees Celsius. Calculate KEQ at T1. And at T2, the volume of the system is halved. Continue the graph to show how this change would affect equilibrium and how the system would respond to the change. Okay, let's walk through this together. So I know my equation, and I know at T1, I can read this out. This is going to be at 1.5 there. And here we're at 5. Thing to note, the units are in 10 to the -2 molarity, which means our N2O4 is 1.5 by 10 to the -2. Don't forget, don't be the silly goose who forgets to look at the units. Make sure you read that because that's an easy mark you could very simply lose. But our NO2 is at 5 molarity. So here, because it's N2O4 at the top, and there's no coefficient, it's just like that, and NO2 down the bottom is a coefficient of 2. This is M divided by M squared, which gives us M to the -1. We put all our numbers in, and that will give us a total of 6.0 per mole. And that's simple as that. Now, the volume halved means, very simply, our concentration doubles. So this is going to happen instantly. If our volume's halved instantly, our concentration is going to double instantly. So at 1.5, we're going to jump straight up to 3. And at 5, we're going to jump straight up to 10. But I guess the question is, okay, what happens next? Well, we've halved the volume, which has increased the pressure. Now, as we talked about earlier, the reaction favours the side that produces the least amount of particles, which is the forward reaction. So we're going to produce more. We're going to produce more of this one here, and we're going to of our product, and we're going to slowly lose some of our. We've gone up 1, so it should go down by 2 here, and we're going to slowly lose some of our reactant. Now, the thing is that we have to note is that the VCAR, this is the VCAR question. VCAR stated, so you jump it up, you get a mark for jumping up to the right spot from 5 to 10 and from 1.5 to 3. But you have to also, when going down and doing this slope, had to be in the right molar ratio. So this is a gap of 2. This is a gap of 1. And that's because we produce 1 N2O4 for every 2 NO2. So that was a mark that that's something they required you to do to get that mark. Yeah, so the change in NO2 is double the change in N2O4. Alrighty, and that concludes Unit 3. Simple as that. Now what we're going to do briefly is a bit of a Q&A. Nonan, are there any questions from the chat that are quite pressing?
No, not in the chat at the moment.
Okay, fantastic. So let's go through and let's do some of the questions from here. So where are we? Share screen. Here we go. Okay, so hop onto the Menti, ask your questions, ask away. All right, so should we get the short answers first instead of multiple choice? Nan, do you mind taking this question? I'm just going to fill up my water. That's okay.
Well, what I did first was start off with the multiple choice, but you can try it out in your practice exams and see which one suits best for you. Yeah, and I think because we work differently, so but I would do multiple choice first and set a time limit and try to do as quickly as I can, but with high accuracy as well, and then move on to the short answers because it takes longer.
Fantastic. Yeah, I think that's a really good point, Nan. I think essentially do what works best for you. Try both. I personally did short answers first because I'm like, end of the day, if I run out of time, I can guess the multiple choice. If I guess 20 multiple choice, I probably will get 4 or 5 marks, but I can't guess short answer. But that being said, that's not a method. You shouldn't go in thinking, okay, I'm going to guess these. For me, it was an emergency contingency because I'm a very anxious person. Try both. Do one exam one way, do another exam the other way. Try again. See what works best for you. Fantastic question. What tips do you have for completing the exam in time? I don't think there's anything you can do in the exam that makes it better other than reading time. Read all of the short answer, and then start working on the multiple choice that you can quickly just answer off in your head. I think what it comes down to is practice. Every question in the exam, with the exception of 1 or 2, is going to be a repeat of some style of question. Not the exact same numbers, obviously, but some style of question done in previous years. The more questions you do, exam questions, not textbook questions, exam questions, the better prepared you'll be, and you won't have to sit and think about the method going about it because you've already done it and you know it. Nan, do you agree?
Yes, I agree. Like last year in my reading time, I read through the short answers first, and then I moved on to the multiple choice and then worked out the answer in my head. So when time start, I can just circle in the answer, and it saves time.
Fantastic. Why is distribution of kinetic energy not a bell curve? I can't give you the exact answer, but it's just because in real life, we talk about methods, everything's a bell curve. In real life, it's not. Very few, in a typical circumstance, very few products. Imagine if everything in like the world is suddenly colliding and creating new things all the time. I mean, it kind of does, but it is not distributed as a bell curve at normal temperatures, essentially. But again, you don't need to understand the process behind. It's more understand the fact that only some collisions are going to be successful because only some are going to have enough energy to react. How do we access the recording and slides? I think we'll come to that one at the end, and we'll go through that at the end. I think we'll just stick to content just for the moment. Is it enough to do just VCAR exams? Yeah. I mean, you don't have to. I mean, I know people who've got a 50 study score doing no VCAR exams. That being said, it doesn't mean that was a good idea. I know people who got 50 study scores who did every exam under the sun possible, like did HSC exams, did Northern Hemisphere exams, did all these different other company exams. I don't think it's like companies that get you an exam mark. It's how well you work, the questions you expose yourself to, and the actual process. So it's all good and well to say I've done 100 exams. Who cares unless they're proper? So I know in my year 12, people would say to me, I was doing literature and I would do 1 essay every 2 days. So literature exam is 2 essays. So I do an exam of every 4 days from swap back. Some of my mates were doing English mainstream were like, oh, I'm doing 1 exam a day. Like I'm doing 3 essays. Like, Josh, you're not gonna do very well. And I had to think about it, and I actually did do very decently in literature. But that's because every time I'd spend more time on something, but some of the time I'd spend on that exam or on the exam would be going over and rereading everything and going over my content. I'd do the same for chemistry. I'd map out where I was making mistakes, because you can do 20 exams or 100 exams. And if you're doing the same mistakes again and again, or you're not going back and marking and critiquing yourself, nothing's going to change. So some of my mates, they just do as many exams as possible. People that are doing with solidifying bad habits. Whereas I like to think I was going through and thinking, okay, that's where I've lost marks. Okay, that's what I'm going to do to change next time. That's the best way to study, in my opinion. Look at how you're doing, look at where your issues are, and think about how you're going to change those. For example, I always thought I was really bad at organic analysis, and then I couldn't understand why I kept on missing a few marks in the exam, every single exam I did, and in my practice exams. And I went through and then I decided to map out every single question in each exam I was doing in terms of the content. And it turns out I was actually getting all of my organic analysis questions right. It was the electrolysis questions, which I thought I'd aced, that I was getting wrong. So the electrolysis questions, I would then focus on, did a few textbook questions to get at my skills. Because I actually couldn't critique myself. And after I started doing that, I was routinely getting 98 to 100% on my practice exams. So self-criticism is really, really important. Awesome. Now, I can do a couple more questions. University textbooks, no, I don't recommend reading university textbooks. If you want extra scope of knowledge, great. If you're enjoying it, great. But remember, VCAR gives you a list of things that are going to be in the exam, essentially that study design. And they say these things. They say like non-branched esters. So you won't ever have esters with other functional groups. They say, like 2 functional groups per molecule. University chemistry goes into a lot more detail into how, your reaction pathways take place. And I think it's just a bit too far, unless you've got a genuine interest in it. In terms of doing well in chemistry, no, it's not going to help you. It's not going to provide any benefit. Because remember, the standard it's not measuring how much you know about chemistry. They're setting how well have you revised for the study design. And the study design is aimed for year 12 students. How can I increase my understanding of the content and maximize my marks? Go through workout, again, it's saying, go through workout where you're going wrong. Attend written lectures. Oh, fantastic, you're here. And go through, if it's areas you're struggling, go through back to your textbook and do those key skill questions. Your exam revision should be only exam questions, but your skills revision should be textbook questions, in my opinion. No, I'm sorry, I've been talking my mouth off. Anything you want to add?
No, you covered everything really well.
Oh, thank you. I'll double check that. My understanding is 100 kilopascals, but I may be wrong there. Concepts of isomers, yes, important, which we're going to cover in literally a minute. How much time do you spend on multiple choice? I would spend 20 minutes to half an hour, personally, at the end of the exam, personally. But no, how much time did you spend?
I don't remember. I'm pretty sure around 30 minutes or I tried to finish within 30 minutes.
Great. Awesome. How do we share the time heat combustion? I think we'll cover all of the content stuff. Yeah, I made a mistake book. Yeah, I did, exactly. Making mistakes book is really, really important, I think, in my opinion. Alrighty, so let's jump back to our fantastic content for today. Now on to the big stuff, and awesome. Alrighty, from current slide, and I'm just gonna swap. Here we go, organic analysis. So I have all our chemicals here. This is just second from Wiki, where we have all of our general alcohols, ketones, aldehydes, carboxylic acids, ethers, esters, amines, and amines. So a couple of naming priority things. So a double, triple bonds are never combined in the name, and halogens never take priority. How are we going to go about naming molecules when they come up? I'm jumping straight in. Identify all the functional groups and branches. Identify the length of the longest chain, the parent molecule. Add the priority suffix and add the prefix attached to the number carbon. Add the names of alkyl branches that are added. And if there's more than one group, use di, tri, or tetra. I think someone's got their hand raised. If you've got a question, feel free to pop it into chat or the Mentimeter. Thank you. Okay. Great stuff. Okay, so I think we've got to understand a few key concepts before we jump into the actual chemistry. So we've got intermolecular and intramolecular bonds. Intramolecular bonds are bonds between atoms inside a molecule. These are the ionic bonds, the metallic bonds, covalent bonds, and where our covalent bonds shared, we've got to remember shared electrons are not equally distributed. And that, for example, in a carbon-hydrogen bond, the carbon is more electronegative, means it attracts the electrons more, slightly more than the hydrogen atom, which is why we say in this bond here, carbon, hydrogen, we've got the one electron from the hydrogen and one electron from the carbon that's being shared, that's going around, but because the carbon attracts it more, we say this is slightly negative and this is slightly positive. For example, in certain cases, but that's why we have, for example, an OH bond, C double bond O, that's why it's going to be like that. Whereas there won't be that case if it's a carbon-carbon bond, for example. Then we have our intermolecular bonds, our bonds between molecules that determine a substance properties. So our dipole-dipole interactions, our hydrogen bonds, and our dispersion forces. So isomers, we have constitutional isomers, which differ in connectivity, but the same elements in the same amounts, but a different construction. For example, we've got butane here and 2-methylpropane. So you can see they're both C4H10, but they're configured different ways. But then we have stereoisomers, which can be enantiomers or geometric isomers. Enantiomers occur due to a chiral center. So you imagine you've got your hands here, your hands are mirror images, they look identical, so they mirror. But if I try to put one over the other, it doesn't work. I've got my thumb sticking out on the other side. So this is what happens here. So you can see here that these two molecules look the same, except here our nitrogen is closer towards us than this side, and here our nitrogen is further away. That's what those dashed lines mean. And so if we try to fit them over each other, one would be like a staircase going up from right to left, and the other would be like a staircase going up from left to right. So it doesn't really work. And this is actually a very important one because, my understanding, this is actually a drug called thalidomide, which is a very, very toxic drug that was used to understanding 3D properties comes more into food chemistry. But one side of the molecule was a very powerful sedative that like helped people relax, and the other was very, very toxic. And the same thing happens with a lot of like pesticides, for example. One side works, the other side doesn't. Or even like peppermint and something. The enantiomer of peppermint, I think, is very, very toxic. Or peppermint flavoring, I think. But essentially, this 3D structure is critical to how it works in the body. And that's due to the chiral center. So a chiral center is anywhere where we have essentially a carbon that has 4 different connections. So it won't be a hydrogen, it would be like another carbon, a hydrogen, oxygen, and a nitrogen, for example. So you can see here, this is a chiral center, just here, because we've got nitrogen, we'll have a hydrogen, we've got a carbon, and we've got a carbon oxygen. So that they're different. But then we also have geometric isomers, where we've got a carbon-carbon double bond, and they're quite weak, but they stop essentially everything from twisting around. And if we have a functional group, let's say this here is our functional, like we look at it like this, these are two group, or this is our, here, not a functional group, sorry. The way the molecule is located, it's going to go here, here, and then here. This creates a C, or a U, but a sideways C. This means it's cis. But if we go here, 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 like a Z, that is trans. So that just describes what side of the, if both carbons on the same side of the chain of the double bond, it's cis. If they're different, they're trans. Alrighty. Let's jump into a bit of substitution reactions. Essentially, in this reaction, one halogen atom replaces or is substituted for a hydrogen atom. And it requires UV light and heat. Reactants are often an organic compound plus a halogen gas, and essentially we swap one hydrogen atom for a halogen atom, and that can produce different isomers. So for example, if we've got propane plus chlorine gas with UV light, our chlorine could jump on to the end there and become 1-chloropropane, and then also our HCl gas or liquid, or it could jump in the middle and become 2-chloropropane, which is, and then our HCl gas. So it can definitely produce isomers. Because the halogen atom is very electronegative, the carbon attached to the halogen is partially positive and therefore is susceptible to further reactions with anions. So this here really likes the electron. So it drags it, which makes that bond very weak, which means if you've got a hydroxide ion, it can just come along and jump right on. Here's just a bit of an example. We've got methane with our chlorine gas to get chloromethane, and we can keep adding chlorine gas until we get tetro. So 1 is going to be, there's no prefix. 2 is di, 3 is tri, and 4 is tetra. Awesome. Now we have addition reactions where essentially in this process we've got carbon-carbon double bond, addition is double bond, and we add them to the molecule. We don't replace them. If we add a halogen gas, so Br2, we'll produce a saturated alkane. So we'll get our bromine, for example, will attach to both carbons and create 1,2-dibromoethane. We add water, it will make an alcohol because it will go to H plus and OH negative, but that requires H3PO4, a very acidic environment, at 300 degrees Celsius. If we add hydrogen gas, that's when we'll form a saturated alkane, and that will happen instantly. And we can also create polymers, like polyphene. If we add a bunch of them together and a high temperature pressure and a catalyst, we create polyphene. And polyphene is denoted, if we write it out like this, and we say 10, that means there are 10 units that are 4 long. The other way we'd write it is just like this. Just do the 1 with the lines outside, and we do 40. So that'd be the same thing. So 40 units of monomer. Awesome stuff. So essentially we have C2H4, we have bromine, it's going to become CH2Br, CH2Br, HCl becomes CH3, CH2Cl, H2O become ethanol, and a pressure on the catalyst will become polythene. We now have oxidation reactions, where essentially alcohols can be oxidized by strong oxidants, not any oxidant, strong oxidants like acidified permanganate, and it has to be acidified, or acidified dichromate. And they produce aldehydes, ketones, or carboxylic acids. Now, this is key in a primary alcohol. So primary alcohol means that the carbon that the oxygen is attached to is only attached to one other carbon. So a primary alcohol will produce a carboxylic acid. A secondary alcohol with it, so there's a carbon on either side, will produce a ketone because that's going to go to a double bond oxygen. And a ketone is the carbonyl group, so C double bond O, in the middle of a molecule. But the thing to note is that technically, this primary alcohol will actually be oxidized to an aldehyde, which will then be oxidized to a carboxylic acid. That's the thing to know. We can say that sometimes in questions, it's a bit confusing. They'll say the alcohol goes directly to a carboxylic acid. Other times they'll say it goes to an aldehyde and then to a carboxylic acid. But essentially, all you need to know is primary alcohols will become aldehydes and carboxylic acids. Secondary can only become ketones because you can't have a carboxylic acid because there's not enough space for the bonds. Awesome stuff. So esterification is another key reaction. We've got a carboxylic and an alcohol that becomes an ester and a water. So it requires H2SO4, and because it's a very low yield reaction, it requires a very acidic environment. So it must be a liquid. So H2SO4 liquid, we need to write down as, or concentrated H2SO4. But essentially, in VCE chemistry, we only have simple esters, so there'll never be other functional groups or branches. Another thing to note is that there's very strong dipole-dipole bonds, but they cannot form hydrogen bonds with themselves, whereas carboxylic acids can, esters can't. We have amine. Amines are our fancy group with our NH2 on the end. That's an amine. And a primary amine is like an alcohol. They're very similar to alcohols. Primary amine is what the end of the molecule, secondary is in the middle, along there. And we can combine this with a carboxylic acid in a condensation reaction to producing water. And that will produce an amide. Whereas with esters, we join our carbon, we join with oxygen, we get rid of another OH. Here we get rid of the OH and get rid of one of the H's to produce water, and the N joins straight on to the carbon. And it requires high temperatures. So amine groups behave similarly to hydroxyl, so to alcohols, but amine condensation will only occur in VCE chemistry with a primary amine because it can happen in other senses, but we don't care about that. It's only going to be like an ester essentially. But here we get an amide link, an amide here, so CONH, which is very, very cool. So quick question here. It'll be great for everyone to pop into chat what they reckon is happening. What is the systemic name for the molecule above? Well, we've got that molecule there. So give it a go. I'd love to see people pop some stuff in chat. Now, this question here, only 44% of the state got it correct, so it's a bit difficult. Awesome stuff. So let's go through. So what do we have? We've got, let's find our longest chain. So 1, 2, 3, well, 4, sorry. Or we could say 1, 2, 3, 4, either way. This here is going to be it's going to be butanol. Now we react it to create a acid, which means we're going to get rid of one of these, essentially. Get rid of those two H's. So it's going to be a methylbutanoic acid. So we can get rid of the pentanoic because there's no straight line, but we've got a methyl group added on. Now we always count from, our carboxylic acid is always our most important functional group, so we count from here. 1, 2, 3, therefore it's just 3 methyl, so attached to the third carbon, 3 methyl butanoic acid. So the answer there is D. I've got a quick question that we'll go through briefly. The following pathway describes the preparation for a certain ester in a laboratory. Draw and name and draw the structures of product X and Y. Draw the skeletal formula for butyl propanoate. Write the chemical formulas of propionate substances for region A and region B, and write the chemical formula of the inorganic compound produced at the same time as product X. So we start with 1 chlorobutane and 1 propanol or propan-1-ol to produce butyl propanoate. All right, give this one here a go. Awesome stuff, everyone. Okay, let's run through these answers. So name and draw the structures of product Y. Okay, so product X and Y, we're producing an ester. So one's got to be an alcohol and the other a carboxylic acid. Alcohols can be produced by substitution or addition, and acids from oxidation. Therefore, we have propanol, we already have, so we could keep that, but we can't go from butane straight to a carboxylic acid. So we're going to go, Y must be the acid, and X, we can convert that easily into an alcohol. So we have chlorobutane, 1 chlorobutane, and that becomes, oh, I'm a goose. No, I didn't. No, I'm fine. No, sorry. And that becomes butan-1-ol, which is product X. Now we have propanol, or propan-1-ol, and that's going to become, always happens, always forget to throw my animations. So there should not be a hydrogen there, so that's silly of me. But that's going to become propanoic acid. Skeletal formula of butyl propanoate. So how we draw these is I like to draw it out, but each skeletal formula, each point represents 1 carbon. So we got butyl propanoate. So our propanoate is this side, so 1, 2, 3. So that's our propane. It's got the double bond oxygen. This isn't a carbon, it's an oxygen. We got 1, 2, 3, 4 to produce our skeletal formula there. So it's really just drawing it out, but with lines instead of drawing the carbons and the hydrogens in. And write the chemical formula for appropriate substances. Well, region A is using the substitution reaction where chlorine is replaced with hydroxide. Therefore, A must be a hydroxide salt. So we can do KOH or NaOH. Region B is involved in the oxidation reaction of a primary alcohol. Therefore, it must be a strong oxidant. So acidified dichromate or acidified permanganate. Write the chemical formula for inorganic product. Now, this depends on what you used for that. For the region A, essentially, if I was using NaOH, it would become NaCl. Or if I did KOH, it would become KCl, for example. Alrighty, so let's jump into the final big part of today's session. So skeletal formulas, the question there, skeletal formulas removed from the study design after last year. Look, they were added back in last year. I was taught them I would always recommend knowing them personally. I think that there's no benefit. There's no detriment to not know. Well, there's no detriment to knowing them. There's no benefit to not knowing. I think I think they're a bit of an asset to use. And I'm pretty sure I have seen them on previous exam questions before. So yeah. Alrighty. So spectroscopy now. To answer a few more questions that have come up, is it important to remember specific catalysts and regions for all the reaction types? Yes. Yes, it is. You will be asked. How to memorize them? What I would do, I would draw a big map. Start off with 2 random molecules and draw a big map of everything that can come from those molecules with all of the regions and everything like that. I think that's probably the best way to do it. All right, anything related to the content. If asked to draw the possible isomers of an alkene, should you include its corresponding cyclic alkane? Well, no, because if it's a cyclic alkane, it won't be an isomer because it's going to have a different number of hydrogens. Because remember, you're taking up 1 bond, you're taking up 2, because it's a circle, you'll be taking up more bonds than you should with an alkane. So it's going to have at least 2 less hydrogens. So you won't ever draw a cyclic alkane because it's not an isomer. Awesome. Alrighty. Yes, you can donate a primary alcohol going straight to carboxylic acid. That is okay. Fantastic. Okay. So, awesome stuff. So IR spectroscopy. So essentially bonds between atoms in molecules are different lengths and strengths. For example, carbon-oxygen is a stronger bond than carbon-hydrogen, and carbon-carbon single bond is stronger than a double. Bonds absorb different wavelengths of infrared radiation. So we shoot radiation in of different energy levels, and they absorb different ranges. So here we shoot in all this energy, and some of the energy, we get the energy out, but some is disappearing. So you can see that 50% of the energy has been absorbed, or down here nearly 90%, more than 90%. And we know that certain with IR spectroscopy, we know that certain functional groups correspond to certain frequencies of radiation. So this here is the energy that's absorbed. For example, we know CO is corresponds to this region here, C.O. Now, the question applications, that's part of the study design. Applications of IR spectroscopy include identification of structures of large and complex molecules in the lab, complex drug percentage impurity, and blood alcohol content and CO2 monitoring. So here we've got a variety of different IR spectra, but essentially multiple molecules may have identical functional groups, but the spectra will be produced will be slightly different due to the different placing of carbon atoms. Now, IR spectra, you don't need to be able to distinguish different molecules, just identify which functional groups are in there. Now, don't try and identify every peak. We have the functional group region here, and the fingerprint region, just don't bother with. We know that this big one is always going to be there. That is the CH stretch. That's always going to be there. And some bands may overlap with other bands. For example, OH and NH. There's always, I remember seeing an awful question about OH and NH in the same molecule, and you couldn't tell because the OH eclipsed the NH. And neighboring groups in the molecule may slightly shift the absorption band than expected. Obviously, all of the information on what's where is on the study, is on the data book. But if we go through here, we can see that here we've got hexanoic acid. Now, points out key signs. You've got the classic icicle, it's called the icicle of carbon double bond oxygen at around that 1600 mark. And we have, just like here with the 1-butanol, we've got that OH, but in a carboxylic acid, the OH moves to the right and merges in with the CH. Here, butanol, we have the carbon double bond oxygen. It's got the same spike there, but we know it's going to be in either an aldehyde or a ketone because there's no curves there that signifies the OH group. And finally, NH is also very similar, but NH is in the exact same spot as OH, except like N somehow reminds me of like nitrogen, reminds me of like it was produced by dying bodies, so it makes me think of vampires, and this here is like vampire fangs. And that's different. Whereas a OH is smile, whereas vampire fangs are for NH. Aldehydes, ketones, and esters, you won't be able to tell the difference between aldehydes, ketones, and esters. in IR. Really, S you'll have that other oxygen group, but you won't really be able to tell the difference at all. Like that's the point. Like IR, you can't use one of these to identify a molecule. Here we have NMR, where essentially we do the same sort of thing. We apply energy into the molecule and see what it's absorbed, except previously we're doing IR energy and now we're doing radio waves. And essentially the radio wave is applied to compounds that impacts the spin of the nucleon. Spin is just a state. And essentially all you need to know is that when spin changes, they'll achieve resonance, and resonance is associated with different environments. So different environments in the molecules. And so again, the energy required to achieve resonance is also affected by neighboring atoms, but we know what environments cause what resonances, therefore we can kind of map it out. So identify the number of carbon and hydrogen environments in each of the following molecules. Give this one a quick go. Some music on. Awesome stuff, everyone. So let's briefly go through. Here we're going to have different carbon environments. So carbon environments are identical if they can be replaced and swapped with each other, nothing changes. So for example, here, this carbon is the exact same as this carbon, exact same as this carbon, whereas this one in the middle is different. So we've got 2 carbon. Hydrogens, we've got 1 hydrogen attached to an oxygen, and all the rest of the hydrogens are attached to the carbons are identical. So we've got 2 hydrogens. Here, we might be like, oh, okay, we've got CH2, CH2, they're the same. No. This CH2 is connected to a C, that's connected to an OH, so this one is a C and a C. So here we're going to have 4 different carbon environments. So 1, 2, 3, 4. And hydrogen, we're going to have 1, 2, 3, 4, and then the one on the oxygen. So actually going to be 5 hydrogen. And our final one is this here, 1, 2. Now these 2 branches are identical, so we're going to have 3 in total, 3 carbons. We have 1, 2, 3, 4 different hydrogen environments. So the first of 2 hydrogen environments. Oh, yeah, first does have 2 hydrogen environments, I think, here. I'm not sure what people are saying in chat, sorry. Awesome. Okay. Fantastic. Okay, so let's jump on. So here, the basis of NMR spectroscopy is essentially we use this chemical called tetramethylsilane, which is chemically inert and it has a shift at 0. And essentially that just gives us standards, so don't worry about that. In proton NMR, when you look at hydrogen environments, we produce splitting. And the splitting essentially is the number of peaks, the splitting for the number of peaks in a proton environment is n+1, where n is the number of protons present in adjacent environments, in environments of adjacent carbons. So for example, I'll show you a question in a second. We've also got high res and low res, and that's these exact same. So this is methylpropanoate, and you'll just see that the areas are distinguished in low res, whereas high res, it's actually peaks. So low resolution can't distinguish between the various individual peaks, but the ratio of areas underneath the curve can tell us the ratio of numbers of hydrogen present in that environment. Awesome stuff. So, for example, here we have 1,1-dichloroethane. So you can see every single hydrogen is connected to a carbon bonded to CHCl. So there's only going to be one single peak. Whereas here, if we've got these ones here, is the one dichloroethane. So they're both the chlorines in the same molecule. Our first one is going to have a shift down here, and it's got 2 peaks, whereas our second one, our orange, is going to have a shift all the way up here. It's got 4 peaks. The reason why is because this hydrogen environment is bonded to a carbon, and the adjacent carbon has 3 hydrogens on it, which means n plus 1, n is 3, is going to be splitting 4 times. So we've got 4 different peaks. Whereas these ones in red, their adjacent carbon has 1 hydrogen attached to it of a different environment. N plus 1, n is 1. There's going to be 2 different splits there. Fantastic. And finally, the big one is the mass spectrum, which is really, really difficult, I always found. But essentially, in mass spectroscopy, we have a molecule and we bombard it with an electron to make it charged. And that's very unstable now. And the unstable ion, so we bombard it with an electron, and that it hits a molecule that takes off another electron and becomes a cation. And it undergoes fragmentation. Essentially, and different fragments will appear. So the tallest one is the most common one, and that's the base peak. So the parent peak is often the highest one. And you've got to remember there might be some isomers in there, isotopes in there that might increase the number of some things. So I've got a brief question here. What I might do is, just for the sake of time, I just want to smash out with the content. I might come back to this one here, but there'll be answers included in the slides. Actually, I'll go through this one, and no, I will go through this one now. Okay. Sorry. A chemical that contains carbon, nitrogen, hydrogen in a 4:1:11 ratio is analyzed. We've got all of these different things here. So in the IR spectra, there are troughs at those 2 numbers, right? The bonds responsible. Or if we go back and have a look, sorry. Go back and have a look in the R spectra. We have the vampire fangs at 3,000, at 2,000, and at 3,300, sorry, 2,900 is going to be CH, 3,300 is going to be the vampire fangs. So that's going to be CH and NH. Using the mass spectra with a peak at 73, determine the molecular formula of the parent molecule. Well, we know that we have an empirical, so we have C, N to H is 4:1:11. So for every 1 nitrogen, there's 4 carbon and 11 hydrogen. Let's find out that molar mass. And that just so happens to add to 73. Therefore, the formula is very simply C4NH11. So, using the mass in the R spectra to draw 2 possible isomers, so essentially we know there's going to be a amine group somewhere in there, an NH group. So it could be anything like this that has 4 carbons, 11 hydrogens, and 1 nitrogen. But now there's chemical shifts appear at certain locations in the carbon-13 spectrum. Draw the skeletal form of the molecule that's consistent across all 3 spectra. And note that this question includes mass spectroscopy and skeletal formula, so it predates the inclusion of skeletal formula in last year's study design. So 20 responds to those 2 environments, and 50 responds to those 2. But there are 3 carbon environments and 4 carbon atoms. Therefore, 3 carbon environments and 4 carbon atoms means we must have some sort of branch, because it's an NH, which means it's not going to be symmetrical. You've got to have some sort of branch. So it's going to be like this, and we just got to figure out where the N is. But as it's shown, the NH2 is at the bottom there. Feel free, it's a tough one, feel free to go through that in your own time. Now, chromatography is also a very important thing, where we have a stationary phase and a mobile phase, and we put things in. The stationary phase is usually non-polar, mobile phase is usually polar, but it could be the other way around. But how strongly a component adsorbs to this mobile phase gives us its, and stationary phase gives us its polarity. So a non-polar molecule will more strongly adsorb to a polar stationary phase, polar mobile phase, polar stationary phase, and a non-polar molecule will more strongly adsorb to a non-polar stationary phase than a polar mobile phase, whereas a polar molecule will move further up with the mobile phase. And there's different types, and the big one is HPLC, where we have qualitative analysis, where we don't know what the chemical is, we put it through a machine and we compare that to other things. So for example, here, we've got aspartame, and you can see the peaks match up. So this is like if I'm putting Diet Coke in, we get aspartame and aspartame there. So we don't know that one there's aspartame, but we've got a pretty good guess. But qualitative is the area under the peak generated by the chromatograph. So we know what it is, we don't know what concentration. So we put known standards of known concentration in. We create a peak area by concentration, and that will tell us. And then if we have an unknown and that fits somewhere on that line, it will tell us exactly what concentration it is. And the final big one is titrations, where the things to note, I'm sure we've all been over titrations, but the equivalence point and the end point aren't the same. The end point is a point at which the solution changes color. The equivalence is when it's being neutralized. We want to get those as close as possible. The things to note is that the burette should be its final rinse should be with the acid or base being titrated. The pipette, it should be with a solution that will contain the aliquot, and the conical flask should be with deionized water. Those are some big key things. So, we just want to note that acid-base titration. So redox titrations act as the exact same way as acid-base, but because back titrations aren't examinable, they will only include calculations for MSc redox titration. Exactly the same as acid-base, essentially. The thing to note, we've got a whole lot of different acid-base indicators. This is just because, for example, here we've got a strong acid and a strong base. Our volumetric flask contains a strong base, very high pH. We drop enough acid and boom, it hits. So if using phenolphthalein will tell us when it hits there. And the line's pretty straight. Like it's only 1 or 2 drops to actually change a pH from like -3, like from 10 to 3. So phenolphthalein or methyl orange is both fine. But for something like here with a weak base and a strong acid, the phenolphthalein we wouldn't use. We'd use methyl orange because we want it near as possible to the equivalence point. Likewise, we wouldn't use methyl orange for a weak acid and a strong base because it would never get to that pH. And both are pretty bad for a weak acid versus weak base. Alrighty, so we're going to briefly watch another video, take a very quick break before we finish up, just a bit of food chemistry for today. So watch a quick video, have a 5-minute break, and then jump back into things.
Hi, my name is Sahaj, and I'm an investment banking analyst here at UBS. So basically, I work with the team to advise our clients on making important decisions, such as how to use their resources most efficiently, how to grow the business moving forward. Is it a good time to sell a part of the business? Is it a good time to maybe buy another business? So we help them with these decisions. What I've particularly enjoyed in my short time here at UBS so far is the opportunity to work for some pretty big companies that I'm sure would all deal with on a daily basis. So I think it's really cool to be a part of something like that. So during VCE, I particularly enjoyed math and commerce subjects. So I studied maths methods and specialist maths. And for the commerce subjects, I did accounting and economics. I was really interested by what I learned during VCE, so I wanted to pursue it further. And that's why I studied commerce at the University of Melbourne. That's where I learned about finance. I involved myself in a lot of university societies, and that sort of sparked my interest in investment banking and the work that we do here at UBS. Some additional advice from my end is always to be curious and to not settle for things. And whether that's with your career path or what you might want to study in the future, make sure that you're always trying new things and opening your minds to everything that's out there. I guess VC is just one chapter of what can be a pretty long story. So whether you perform exceptionally well or not in a couple of months' time, remember that you still have the rest of that story to write. My advice to myself, if I was doing VC again, would most definitely be to zoom out and always take a look at the bigger picture. You've probably heard something like this before, but high school's a very unique experience, I think. It's definitely one of the last opportunities for you to spend almost every day with a majority of your friends all around you. Make sure not to get so consumed by VC that you forget about what's otherwise a really special year in your lives. Don't forget about your passions, your development as a person. So trust that you've put in all the hard work for your VC exams, give it your best shot, but look forward to the life ahead and everything else that's exciting in your lives.
There you go. Wonderful. Thanks to UBS for that. Alrighty. So we're going to take a very brief break. Put some Leah here. Fantastic.
So I have to admit this, and I know it's not cool to admit this, but like when people talk about deep breathing and breathing exercises and watching your breath come in and out, like I literally go, oh my God, I don't know if I can do this. Like, I don't know. That is completely on me. Like, that's totally on me. I just don't get something. But there is an element of our breath that I've learned something about that, like, seriously, it is super cool. So here it is. When we're feeling really stressed or really anxious, like when something's really important to us and we want to perform well, what happens to our breath is that we start breathing really shallow breaths and lots of them instead of a few breaths and really deep breaths. And the more stressed we feel, the more shallow the breathing is, so basically stops about here, the more frequent the breaths are, and they start to be these like really short, shallow breaths, almost like we're panting, which can lead to completely hyperventilating, like in full-blown anxiety. So here's the thing that I really love. Our breath is one of those things that we do automatically, like we don't have to think about breathing, we will automatically breathe, but it's also something that we can control. So it's something that we have a say over. Like we don't have a say over how fast our heart's rating. We can do things that can slow that down, but we can't go in the moment. We can't go, okay, heart, I want you to beat this many beats per minute, right? With our breath, it's totally different. We can go, you can take 5 deep breaths and you can change it from going to really long, deep breaths. And there's something extraordinary that just by virtue of the fact that we have control over this automatic system, it actually changes our capacity to speak to our brain when we're kind of freaking out. Like, and most times we don't feel like we've got any way to have our body communicate to our brain, but here we actually do. So here's what you can do. If you find yourself in a position where you notice your body's just doing that stress response and you're breathing shallow, you can actually decide to take a few deep breaths. And what that does is it communicates to your mind that you're okay, because it knows that if you're taking short, shallow breaths, something's wrong, right? That's an instant communication to your brain that something's wrong. And then it wants to step in and deliver you those stress hormones like adrenaline and cortisol, which amps up the stress response, which makes you breathe even more shallow. If you can send a signal to your brain simply by taking a few deep breaths, it'll go, cool, Leah's relaxed, she's chilled out, like there's nothing wrong, just gonna cruise now. Like that's how it works. I hope this helps. I really hope it helps. Let me know.
Wonderful. Yeah, again, Leah's an absolute inspiration. Awesome. Wonderful. Okay, cool.
So
I've got I'm just going to skip through. There's just a question here of for titration, but I'm just going to go to food chemistry to finish up the content for today, then we can always run back and do that one. So food chem, my personal favorite part of chemistry. Easy peasy stuff, very, very simple. In my opinion, obviously it can be a lot of info, but I quite like it. Studying medicine, I think it's quite fun, quite cool. Also, a reminder: keep trumping questions through the chat. Through the Mentimeter. Questions about defining terms. They can ask you to define terms, but focus more on application. And would you ever be asked to explain how IR spectroscopy and NMR spectroscopy works? In the study design, it says that you can be the basics, but not the actual equipment. So I think you have to understand that, bonds absorb energy. That's the basis of it. And then different IR, NMR, blah, 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 like UV, it's all different energy levels that are being shot in, which is going to produce different spectra. Okay, cool. Carbohydrates, right? So we've got glucose. Glucose is pretty cool. Glucose is a type of monosaccharide, mono meaning one, saccharide meaning sugar. And there's glucose, fructose, and galactose. So the 3 major monosaccharides. And the hydroxyl groups on them makes the molecules polar and highly soluble in water. You can put sugar in water, mix it about, and it dissolves. So the monosaccharides are monomers, and the disaccharides are formed between the condensation reaction between 2 monomers. And they produce an ether link. So that's not an ester. An ether is where you've got a carbon, oxygen, carbon, and there's no carbon-oxygen double bond. This is an ether link. In this context, we call it a glycosidic link. We've got three main types of disaccharides: maltose, which is glucose and glucose; lactose, glucose and galactose; and sucrose, glucose and fructose. And there's various enzymes in the body that dissolve this. So enzymes, as I'm sure you know, are proteins that will help metabolize these food molecules. So we've got amylase from in the saliva and in the pancreas, and they require a very basic pH. So in your small intestines or in your mouth, and they break the big carbs down. Maltase breaks down maltose, and that's in your gut. Lactase breaks down lactose, and that's in your gut. And some people don't have lactase, which means all of the lactose is sitting there and can give someone gas and make their stomach quite upset. And cellulase breaks down cellulose, another type of carbohydrate. Now, so polymers of monosaccharides are mostly soluble in water. So sorry, except with the exception of cellulose, starch with amylopectin, amylose, and glycogen are mostly soluble in water. So these are types of polysaccharides. Now, starch which is what, like in our foods, like potatoes, for example, there's two different types of starch. There's amylopectin and amylose. Now, if you can imagine, amylose takes a very long time for it to be broken up because the enzymes sort of come along and cleave this off one at a time. Right? They've got to break it down because they attack from like this. So they break it down one at a time. Whereas amylopectin, a group of enzymes can break down so many bonds at once and convert this straight into glucose. So different foods of starch will have different amylopectin to amylose ratios. And the higher the amylopectin to amylose ratio is, the more amylopectin, that means it's a very low GI, which means a very high GI, which means the glycemic index is very, very high. Glycogen is how we store sugar in the body. So we've got sugar and we store it in our liver in the form of glycogen. The reason why it's so highly branched is because if we're fight or flight, actually as Leo was just talking about, we want to get that sugar straight into our body. So it's very, very highly branched for our enzymes to break it down. The cellulose is insoluble in water and is found in plants. And it is very, very, it is all of these connections from multiple different sites, which mean, and we don't have an enzyme to break it down, meaning we need fiber, it's essentially fiber, but we can't digest it or get energy from it. Next up, we've got lipids. So saturated lipids have no carbon-carbon double bonds. Monounsaturated means there's one, and polyunsaturated means there's multiple. Now, a triglyceride is formed from a condensation reaction between glycerol, which is essentially like your propanol, but with 3 OH groups, and 3 fatty acids, and they create an ester link. And that's called dehydration synthesis, or it's condensation, where we produce 3 waters to produce that triglyceride. But essentially, as the number of carbons increases, the number of dispersion forces increases, meaning melting point increases. But the cool thing is, so we know with double bonds, essentially we're going to create more double bonds means less hydrogens, means less dispersion forces. But in the context of fat, they also produce kinks and bends that limit the availability for dispersion forces. So, for example, palmitic, stearic, arachidic are all saturated, and they can all actually bond with each other very, very easily, like in a fatty solution. With our unsaturated fats, especially arachidonic, which has 4 carbon-carbon double bonds, the double bonds makes it kink around, and it means that even though there's all these hydrogens on the inside, it actually can't form any dispersion forces with other molecules because other molecules can't fit in there. So double bonds decreases melting point because less hydrogens, but also less availability of physical space. And they're all digested by lipase. Now we have amino acids, which are and essentially amino acids are very, very cool. There's 9 essential, 11 non-essential, meaning there's 9 that have to be consumed by us in order for us to survive. And they form like a peptide chain. And that is a condensation reaction. So it's really like it's essentially an amide link, but we call it a peptide link in this circumstance. And it's very, very cool. So if we have a look at a amino acid, I've just drawn out. So this can actually form what's called a Zwitter ion. So in very high pHs, so for basic pHs, it wants to act as an acid. So high pH, this COOH will act like carboxylic acid, and we're going to get rid of that one there, and it's going to become negative. So it's going to donate its proton and act as an acid. But at high pH, as low pH is very acidic, our NH2 group is going to act as a base, and it's going to accept a proton. And at some pHs, at the exact same time, it can become a Zwitter ion, whereas simultaneously is not amphiprotic, which means it can act as an acid or a base. It's not or, it's acting as an acid and a base. And that's essentially the zero ion, which is very, very important for the 3D structure of proteins. So the primary structure, which is just essentially the linear sequence. A secondary structure, and it's the spiraling of the chain, just caused by hydrogen bonding between the different amine groups in the chain. But the tertiary structure is interaction of the variable groups, the R chains in the amino acids. And this involves hydrogen covalent ionic dipole-dipole and dispersion forces. So disulfide bridges is a big one there with covalent. But let's say we have carbon double bond. So we've got a carboxyl group, which is the carbon oxygen double bond oxygen OH. And that can form hydrogen bonds very strongly with other carboxyl groups. But if we were to say suddenly change the pH of the solution from neutral to basic, then those carboxyl groups will then act as acids, donate the protons, and then the bonds will no longer be as strong, which means the protein might unfold, and the 3D nature is so important for the protein. And the quaternary is just an interaction between multiple different peptides. So as we can see here, the shape, the physical 3D shape is very dependent on the R structure, the R chain. For example, with hydrophobic, so with carbon hydrogen groups, we've got water on the outside. Let's say we've got there's water everywhere, but we're going to, on the inside, our hydrophobic groups are going to try wrap around, which is what it's done here. Where hydrophilic wants to get out. We have ionic bonds here, and you can see this NH2. If we were to suddenly put this into a basic solution, an acidic solution, it's going to act as a base, give us NH3, and that may no longer act as properly as an ionic bond, which means this entire thing might unravel. So that's very, very important to consider. And that comes into enzymes. Now, enzymes have a very specific 3D shape that's required. And in that 3D shape, if you ruin the 3D shape, the enzyme can no longer work. Now, this question is going to be in there. I'm just going to briefly talk about metabolism. So essentially, when we eat foods, we go from polysaccharides, we break it down to monosaccharides through hydrolysis, get it into our bloodstream, and then somewhere else in our body, like our liver, we remake it back to polysaccharides. Same thing happens with triglycerides. Breaks down to glycerol and fatty acids, and then reforms as triglycerides to store as our fat. And likewise with proteins, hydrolysis and condensation. So enzymes are molecules. Enzyme and the molecule must bind very specifically for a substrate to bind to an axon site, where the bonds within the enzyme change the composition of the substrate and allow breakdown to occur. We've got the lock and key model, where the substrate fits directly into the active site of the enzyme, this 3D shape, like a key. But the induced fit is where the active site melds around the substrate. But the enzyme, and one enzyme is specific to each reaction, and it's not consumed in a reaction. It can be used multiple times, but it lowers the activation energy for reaction to occur. Now, there's an optimal temperature for it to occur in the body. It's like 37 degrees, and that's because low temperatures, we've got a low rate of reaction, increased temperature, increasing kinetic energy, increased rate of reaction. We get to a point where the kinetic energy is too high, and the molecules hitting each other actually starts to disrupt this giant chain. And it hits the chain, might break bonds, and if the bonds are broken, that means we can no longer have an active site. And if the active site is broken, we can no longer catalyze reactions, which means beyond a certain temperature, high temperatures, the enzyme becomes denatured. Likewise, changing pH will also denature an enzyme. So I've got a quick question here, final question before we move on to some Q&A. In an experiment starch and cellulose, both polymers were crushed in warm water and celery amylase was added. The concentration of starch is measured at different temperatures. Explain why the rate of decrease of starch concentration was less at 50 degrees than 35 degrees, and why there is no change in the concentration of cellulose. Well, amylase performs optimally at around 35 degrees Celsius. As temperature increases beyond this point, the kinetic energy of the enzyme increases, which disrupts its bonds, breaking the intermolecular forces that maintain the tertiary structure, meaning the substrate cannot bind. Hence, the rate of reaction decreases. Amylase is an enzyme specific to starch and cannot accommodate the 3D structure of cellulose. Hence, as there is no enzyme to catalyze hydrolysis of cellulose, its concentration cannot decrease. All right. Vitamins are another big thing that come up, and this is very, very simple. They're organic compounds that can't be synthesized in enough amounts, with the exception of vitamin D, by the body for us to survive. And there's lots of diseases if you have too much of a vitamin or too little. Water-soluble vitamins like vitamin C with the OH groups. If we got too much of them, we just instantly excrete it. We pee it out. But the issue is we need to constantly be eating it because we can't really store it because it's water-soluble. But fat-soluble vitamins are non-polar, so they get stored enough fat. So you can actually have reserves for a very, very long time. But because it's stored and not excreted, the only way we get rid of it is by using it. If you eat too much, it's toxic. For example, if you're ever stuck in the Arctic and you get attacked by a polar bear and you win, you don't eat the polar bear's liver because a polar bear's liver contains so much vitamin A that it will kill you. Just a fun fact. So the final thing in the VCE curriculum is calorimetry. So the first thing I want to distinguish is energy content versus energy value. Energy content is the amount of energy released by the combustion of food, where energy value is the energy available to the body. So not all energy will be available because there may be incomplete absorption, incomplete oxidation, or heat loss to the surroundings. But calorimetry refers to a method of measuring physical heat released or absorbed by chemical reaction. So essentially, we have like a bomb or a solution calorimeter, and we put a food in, we ignite it, and then the water around it, we calculate how much temperature has been raised. The issue is we're going to lose some heat to the metal, to various different things. So what we do is we burn, either we run energy through, and we know that as electricity through, we know how much energy that is, and then we work out the change in temperature, and we say, okay, cool. We know how much energy is required to raise the temperature, therefore we've got a factor that we can apply to our calculations to work out for our food. Or we burn something that we know already, like benzoic acid, and that will give us a calibration factor we can then use. So our final question for today, benzoic acid may be used to calibrate a bomb calorimeter. The reaction that occurs is a combustion reaction. We've got benzoic acid undergoing combustion. When 1.845 grams of benzoic acid is burnt, the temperature in the calorimeter will increase by 33.53 degrees Celsius. Now, so 2 moles of benzoic acid, according to this calculation, will produce 6,454 kilojoules of energy. Mass equals mole by molar mass, and molar mass is 122, which is therefore the mass of 2 moles of benzoic acid is 244 grams. Therefore, 244 grams of benzoic acid is equivalent or produces 6,454 kilojoules. Therefore, divide both sides by 244. 1 gram produces 26.54 kilojoules. Therefore, times both sides by 1.8454. That's going to produce 49.04 kilojoules. So that's the answer there. That's what's released. Now, the calibration factor equals energy divided by change in temperature. So that equals energy, 49.04 kilojoules divided by 33.53. 1 kilojoule, 1.46 kilojoules per degree Celsius. So for every degree Celsius that we were just going to say, every degree Celsius that the temperature is raised by, we have to put in 1.463 kilojoules, or according to the question, 1,463 joules. So that's what a calibration factor is, and then we can apply that to our next question here, where we have 5.59 grams of dry biscuit, and it was burnt in the same bomb calorimeter. The temperature rose from 23.64 to 27.59. Calculate the energy content in kilojoules per gram. Easy. Energy equals calibration factor times by change in temperature. Oh, we just did that equation. So calibration factor, we have 1,463 times by the change in temperature, which will give us 5,779 joules for 5.59 grams of biscuit. If we divide both sides by 5.59, we can then get 1 gram of biscuit creates 1,034 joules, or 1.034 kilojoules. Therefore, the energy content is 1.03 kilojoules per gram. Alrighty. Essentially, we've gone through a lot of the exam skills, but essentially 2 practice exams. Right? We've gone through every bit of content that's possibly examinable today. Got a lot of questions, and hopefully you've seen how we've worked through. Apologies for the rush towards the end. I always overstep my gap in Excel. I like to go into detail. But you guys everyone here has been absolute legends. Questions have been great. Essentially, don't stress. Don't stress about exam stuff. The last thing I want to touch on is just experiment sort of errors. So we've got systematic errors, random errors, just things to know. But the key things I like to ask about is validity. How well does my experiment address the aim is something we really got to consider. Reliability, how similar are my results, just precision. So this is where we have random errors. So we've got to make sure that we do as many things as possible so our results are all similar. Accuracy, and this is affected by how close it is to the true data, systematic error. Alrighty, so we'll do a bit of Q&A, but I just want to check in with everyone to see, let me give me 1 second, how confident do we now feel about the chemistry exam? So give it a go. Please go into the Mentimeter, pop it in, and I will send out Nan, do you mind sending out the feedback link? Yeah, amazing. Thank you. Absolutely amazing to see. We've actually got a huge increase, which just really makes us feel, Nan and I feel really great. Thanks everyone for your attendance today. Just a Skyline hat, we provide weekly tutoring classes, VCE master classes, and VCE mindset programs such as the stress hack. And we'd love to, if you want to know more, feel free to check out the website, which would be great. There's also Leah's exam hack. I would like to stress how incredible that is. And I'd just like to say, ask that everyone just stays for a few minutes just to do the evaluation, please. Really important. Nars just posted a link in the chat. Let us know how we've gone and what we could improve on. And thank you so much for your time today. Make sure to do the survey, pop an emoji in chat when you've done the survey. Thank you. Amazing, thanks everyone. We'll open up the Q&A for anyone who has last minute questions. So feel free to ask away there. So we've got a couple of questions. How do you stay motivated to do chemistry? Nan, do you have any answers?
I don't know, but I guess I find chemistry very interesting throughout my year 12. Which I didn't think so in year 11, but yeah, I think that's the reason why I stay motivated. What about you, Josh?
No, I definitely agree. Also, just before you submit any questions, make sure everyone does the survey link. That'd be fantastic. Look, I think it's one of those things where you've got to find something you like about it. So what I would do, for example, with methods, there was some things I enjoyed, like differentiation I enjoyed, so I do that, try to do that first, and then do use it as a reward at the end, like doing the stuff I enjoyed. But staying motivated isn't like, don't block out like 6 hours in a weekend to do chemistry because you'll hate it. Try to do a little bit every day, I really recommend. And that's a really, really important thing. Would you ever be asked to explain how IR and NMR spec works? I think we answered that one earlier. Do we need to know the exact optimal temperatures of enzymes? No, but understand that the human body requires around 37 degrees. And that 50 degrees Celsius, an enzyme won't be working, pretty much. Yeah. How do we determine sig figs? Look, so essentially on the exam, they ask you sig figs, but there's only going to be one question in the exam, and you'll get marks on for sig figs. So I wouldn't stress about the multiplication, division, all that sort of stuff. I would, like, the only for experiments, sure, maybe, but in the exam-wise, sig figs, the lowest number of significant figures used in the original question is what your answer should be. So for example, if there was like 10.00 and 2.00, and like 3.1003, even though the 2 sig figs is the lowest there, so I'm gonna use 2 sig figs in my answer. Awesome. Fantastic. Any tips on increasing focus span? Take breaks. You can't sit there for 8 hours and just study. Like, you might be like, I need to get this done. You're going to be so much more productive if you block out. I might do 25 minutes of like questions, and then I take a bit of a break, go for a walk, 25 minutes, 25 minutes, 25 minutes, and take a longer break. And then I might do a whole practice exam. Make sure you give yourself opportunity to rest and recover, because your brain is a muscle, and you would be out there running marathons every single day. You'd be training for one marathon.
Yes, I agree. Like, when you think you need to break, just take a day off and don't think about studying at all.
Exactly. Awesome. Can you share the music playlist from the session? Is some new study music? They're all royalty free music you're able to find online. I believe it is Calvin Harris. Alrighty. Thank you very much, everyone, for today's session. Really appreciate all of your feedback and your all of your insight, and also all your participation. We really, really appreciate it. Thank you very much for bearing with us, and best of luck for the exams. You guys are going to absolutely smash it.